I would like to welcome here again Zoltan Kolarovsky.
Thank you so much. Thank you for staying for the next day. Um, okay, so what will be the schedule? We will start with the phase space formulation of quantum optics. However, we have left something which might be important from the previous day. So we might be looking at this thing, which is called the block messiah decomposition, and we will do an exercise like outside of the hands-on session because I think that that will be important for later. So after that we will do the phase space formulation before noon, and after noon we will talk about Gaussian boson sampling itself, and we will execute or simulate Gaussian boson sampling using Picasso, and we will find or we will show a graph theoretical application for Gaussian boson sampling, namely the dense K subgraph problem. Okay. So let's start. I want to revise just quickly what happened yesterday, or what did we learn yesterday. Let me put it bigger. Okay. So what did we learn yesterday? So we learned yesterday about these Fock states and the Fock space which contains the Fock states as basis elements. And we learned about these funny operators, these annihilation and creation operators or ladder operators, and we have shown what is their relation with the Fock states. Also, what we can do is to, um, in order to handle things compactly and nicely, we collected the, um, how do I? Yeah, we collected these ladder operators um, into this vector, which we will which we dealt with a lot. This vector of operator psi, and also we can transform it via another set of operators. This is called the quadrature operators with this W transformation matrix. Anyway, so this is all good. And what did we also see? We also saw that if we have like an interferometer, so this is like an interferometer acting on these ladder operators, then you will get simple transformation rules. So like the linear combination of the annihilation operator will transform into a linear combination of annihilation operators, and similarly for the creation operators, right? So this is like this transformation rule, and from this transformation rule, we have derived the the permanent in this overlap. So if we take like a Fock state um, with occupation numbers n, and we transform it via an interferometer, then we will get some state with the same total number of particles, and the overlap of this with some other Fock basis state labeled by m occupation numbers will be given by the permanent. And we have learned that this permanent is like a very difficult thing, a very difficult matrix function to compute on a classical computer in general. Okay, so this was basically the first part. And what we also saw in the second part, or what we have also dealt with, is these kinds of linear optical Hamiltonians. So these linear optical Hamiltonians are at most quadratic in the ladder operators. We have seen this. And these linear optical Hamiltonians are important for us because they transform very nicely the ladder operators. So we have seen transformation formulas. For example, this how the squeezing transforms the ladder operators. So this is like a squeezing gate. For example, here we can see that the annihilation operator is transformed into another annihilation operator, or like the same annihilation operator multiplied by some cosine h of r, but it also transforms into a creation operator. That is like the intuition behind the fact that it creates particles. Okay, so this is like the intuition, and we had a more general formula for this. So if we have like a strictly quadratic Hamiltonian, then we have this formula here. So this says that the transformation by this strictly quadratic Hamiltonian, or like this unitary admitting this strictly quadratic Hamiltonian, uh, can be described by this symplectic matrix, which we have also defined, but it's like the concrete definition is not really important for us now in this recap. Okay, but we know that we can describe it via a single matrix, and we have seen also, we have seen also that if you give me like a Hamiltonian matrix corresponding to this linear optical Hamiltonian, sorry about the jumping. Uh, so you have this linear optical Hamiltonian. In this linear optical Hamiltonian, the quadratic term, in the quadratic term, or the quadratic term is described by something called a Hamiltonian matrix, which is not an operator, it's a genuine matrix. And we can decompose this matrix. This is quite important, that we can decompose this matrix uh, into like symplectic matrices, or via symplectic matrices into a diagonal matrix. And given like this Hamiltonian, this means that we can like this Hamiltonian operator, uh, we shown that this Hamilton operator can be diagonalized by this symplectic transformation. And we have seen that, okay, because it is like a symplectic transformation, this can be viewed as um, unitary transformation with a strictly quadratic Hamiltonian, right? And we have also seen that the like Gaussian states, so like a Gaussian state looks like something like rho equals e to the minus beta h divided by the trace of something. I didn't include this definition. And we can, yeah, we suggested that, okay, you can diagonalize this Hamiltonian via this linear optical gate, for example. Or I mean, if there is no displacement vector here, uh, then you can diagonalize by this symplectic matrix. Or like, I mean that there is no linear term in the Hamiltonian, it's strictly quadratic, then you can diagonalize it with this symplectic matrix, and this symplectic matrix will become, or it is corresponding to a linear optical gate. So yes, is there any questions so far? Okay, and we have also introduced these this first and second moments. The first one is called the displacement vector, or we call it the displacement vector or mean vector, and there is no agreed upon name. And this is the covariance matrix. And we have mentioned also that if we consider, so this is like the definition, or like roughly the definition of a Gaussian state. And we mentioned that the Gaussian state can be described entirely by this displacement vector and covariance matrix. Okay, so that is where we question.
Yes, I have a question. Is this D matrix here related to with displacement or operation?
You mean this one?
Yes.
No, I mean if you don't have, so if your Gaussian state, for example, does not have like this linear term, then that is not a displaced Gaussian state. The mean is in the center, like it's zero. Uh, but you still have this D. And yeah, so these correspond to frequencies of the harmonic oscillator, basically. So there is this we have already seen that this if you diagonalize this Hamiltonian, or like the diagonalized, yeah, you can diagonalize it something to something like, I don't know, I goes from 1 to D, and you will have these new i's, xi squared plus pi squared u dagger, something like this. And these are operators, and this is basically the Hamilton operator of a single mode harmonic oscillator. And this is like the frequency. Or yeah. But yeah, we don't care about these values exactly for now. Did I answer your question? Okay. Okay. So I think we have finished with the recap, and now I want to um, follow this with the last exercise from yesterday. So in this last exercise, uh, we are asked that we should show that the covariance matrix of a single mode squeeze state is this one. I think this is the easiest one, or the easiest form of this. And how can we show this? We can show this, for example, by looking at the let me remind you how the squeezing gate. So if we transform it with R, I don't consider now complex values here. We consider this one, X and P operators. We can see from in the lecture notes that it is e to the power of minus R and e to the power of R times xp, right? And okay, this is the first thing. And so it doesn't have any linear term. It doesn't there is no identity here or whatnot. Okay. And so this is the first thing. And the second thing is that we have seen already that if you have like this covariance matrix and it goes through some time evolution, so uh, for example, the density matrix goes through some time evolution where U is like a strictly quadratic Hamiltonian. I mean, it has a strictly quadratic Hamiltonian, obviously. Then it will transform as something like this, uh, where S is exactly this transformation matrix of the quadrature operators. Okay. So this was in the last part of the previous lecture. Okay. Feel free to interrupt me if you have any question. And the third ingredient which we will need to use is that the covariance matrix is the identity for the vacuum. Okay. And we can combine these facts because the squeeze state, so here in our case R is like the SR acting on the vacuum state, right? And okay, so this is we know that this is like a unitary with a strictly quadratic Hamiltonian, and we know that the so at this point, so for the vacuum state we had an identity as the covariance matrix. So the covariance matrix of the squeeze state must be, so like let me denote this by 0, and let me denote this by R. This is S of sigma 0 S transpose, but this is identity, we know it, and we know the values, or we know how S looks like. So S is like has this form. It's very nice diagonal form. That's why we chose it. So that's why the covariance matrix is e to the minus 2r, e to the 2r in the diagonal, and outside these are zeros, of course, like here. Is this okay? Is there any question? Okay. Okay. Yeah. So some things there are that you have to accept, but you have to feel that the so the feeling is, or how you calculate this covariance matrices is not to start from like a density matrix and then to calculate the first and second moments. You start from the vacuum, and from the vacuum you can build up your state with squeezings and interferometers and displacements and whatnot. And that induces a transformation on the covariance matrix, for example, here. And then you can just calculate it via the symplectic matrix, which is easier to compute than obtaining the density matrix, or like the state vector for the squeeze state. Actually, I don't even write down the state vector for the squeeze state because it's difficult, and we don't need it basically. So we prefer this picture, this first and second moment, or covariance matrix picture here. Okay. Okay. Question? Okay. So if there is no question, then let me just tell you about the Bloch-Messier decomposition, so we didn't have time for this. And the Bloch-Messier decomposition is a linear algebraic decomposition, which is very useful because it decomposes a symplectic matrix into this form. Like this is the important part, that it decomposes into it's similar to SVD. It decomposes it into two unitaries, V1 and V2, and D, which is not diagonal but block diagonal, right? So you have this one, this is this, and the unitaries are this. And the statement is that this V1, V2 correspond to interferometers. And this D correspond, so these are two arbitrary interferometers, and this D corresponds to a column of squeezing gates. So that means
Sorry, can I be once again angry about notation?
okay.
You write that D is a block diagonal matrix and then D is 2 by 2 matrix. You mean D is block diagonal matrix with these blocks, 2 by 2 blocks, or what's going on here?
No, so you can see that, okay, so it's another use of notation, but cosine h of r is like, yeah, so I should have written it as like, yeah, cosine h of r1, cosine h of rd. So this transpose, this vector, something like this. And
No, now I'm completely lost.
completely lost. Okay, that's good.
Yeah.
Okay. So D looks like this. So cosine h of r1, cosine h of rd. And again, the same here. Okay, and okay, so here you have zeros here. So I put these blocks. I now specify the upper left and the bottom right block, right? And here it's similar. You have minus sine of h, sine sin, sine h of r1, and it goes like this. Okay, and similarly in the bottom left block.
It's not block diagonal matrix by any definition.
It's block diagonal matrix in some basis. Yes.
No, this matrix is not block diagonal. There exists a transformation that produces a block diagonal matrix. Sorry, but this shortcut is very, very, very strong.
Okay. Yeah, I understand. Yes. It's not block diagonal. I mean, if you reorder the elements, then it is like block diagonal, but
So I have a question about this. So is it a version of Cartan decomposition or SVD? Namely that you have some matrix which represents some non-compact group and it is decomposed into the action of the maximal compact component, then there's maximal abelian component, and then second element of the maximally compact component. For example, if you have special linear matrices, yes, it decomposes into unitary, then some diagonal matrix, and also unitary. And here, is it kind of this kind of decomposition or some other?
it is related. It is related. So if you do the Cartan decomposition for the symplectic group, what you will have is exactly like this, that you have like a symplectic matrix, or maybe this is like a long answer. But if you do like the symplectic matrix, then this can be decomposed into how to put it. Let me write it like R and U, which is like very confusing. But the R is like something like purely active transformation. Okay, purely active meaning that there is no passive component somehow. And by no passive component, I mean that in the symplectic matrix, there is like no part which does the passive transformation. And U looks like well, if we look at it in the complex spaces, then U looks like maybe let's not write it as this. Let's be consistent. Let's make it V. This is U hat, something like this. And this is like a purely passive transformation. So this is similar, but it has two components, this decomposition.
Is it like decomposition into Hermitian and unitary in because I mean you have this the composition which is like seems to be semi-similar. Like this R is Hermitian in I mean vague sense. Now I'm hand waving.
Yeah, so exactly if you do the polar decomposition with this symplectic matrix, and the statement is that your unitary in your polar decomposition will be also symplectic, and your Hermitian matrix will be also symplectic. So you will get a symmetric symplectic matrix here. Okay, but we don't use. I mean I don't know if maybe you can derive this decomposition from this fact. Yeah, maybe not. So there is like a derivation for this, which is included, maybe not even included in the lecture notes, but like there is a reference given. So for these decompositions, usually I don't derive in the lecture notes, I think. Yeah. Did I answer your question? Okay. Okay. So this is very interesting. This is all very interesting because that means that okay, you can decompose this symmetric symplectic matrix. That means that I mean if you have like any unitary operator or any unitary operator of a linear optical gate, then you can decompose it as follows. So by this symplectic decomposition, that means that you will have so like you decompose this symplectic into V1D, which is not a block diagonal, but you know this, and on the unitary operator level, it will be something like IU1 times this column of beam splitters, which is written like this, times another interferometer. So I denote I as interferometer, just to not to be confused with the notation. So I is interferometer, and U in its belly is the interferometer matrix, which parameterizes the interferometer, right? So that means that you can decompose any linear optical gate with only quadratic Hamiltonian into these parts. That meaning that it's like your circuit will look like I didn't mean to delete anything. So this looks like in your circuit, you have this circuit, you will have an interferometer U1, and you will have a bunch of squeezing gates, R1, R2, etc., RD, and this goes into another interferometer. This is very good. This is very good because we mentioned yesterday that interferometers can be decomposed into beam splitters and phase shifters. These are single and two mode gates. And we have seen, we can see it now, that essentially you can, so if you have like any Hamiltonian with any quadratic Hamiltonian, you take the unitary of it, you can decompose it into single mode and two mode gates with this. And the only two mode gates, yes.
Excuse me, where to place this displacements in this picture?
In the displacements I didn't mention. So the displacement you have to add because of the linear term in the possible linear term in the Hamiltonian. Like if you want to have like displacement, basically you can put it in the beginning at the end also. So like you can put displacements here. Alpha 1, alpha 2, alpha.
So they commute with this entire part?
No, it doesn't commute.
Um,
So it's a very difficult relation. So to recover the the so if you apply these gates, so if you have like this symplectic matrix, you can recover like the um, mm, quadratic part somehow. And if you have like this linear part, you can also recover independently a linear part. But if you want to merge them together into a single exponent, then you will have to use the Baker-Campbell-Hausdorff formula, which you don't want. So, or you can do it, but I didn't write it down because it's tiresome. So, did I answer your question?
Yeah, okay. So my question now is like from computer science point of view more. So first of all, this is the entire circuit. You don't have to repeat it many times.
Yeah, if you would repeat it like once again, then the expressivity of the circuit would not increase. Exactly.
Yeah, okay. Second is what kind of Hamiltonians, but in the sense of not optics of Hamiltonians, but okay. The question is, how. Maybe you already told it, but I'm not. I was not really. I didn't understand it. What kind of unitaries, generally speaking, can be simulated with them? But the unitaries, I mean strictly in computer quantum computing sense.
So, what kind of unitaries can be simulated? You mean, okay, so
Encoded, maybe.
encoded. So okay, the first thing that I want to point out that these are infinite dimensional unitaries, right? So that is like a big problem. So if you take like the submatrix of it, then that won't be unitary, right? So in that setting you can only consider, or in this setting you can only consider infinite dimensional unitaries, and this is like a very small part of the like a zero measure part of all the possible unitaries in infinite dimensions. So
Okay, but no. The question is, can I simulate the quantum computer, let's say this Wilk here, using this system efficiently?
no, so this is not universal, if that's the question.
Okay, this is not universal. Okay, so do we know, how it is? What are the restrictions? What is the like power of these machines, basically? That would be the question.
Yeah, so that's a really good question because apparently the expressivity is very low. And if you look at it in the phase space picture, then you will, which we will do before noon, look at it in the phase space picture, you will realize that okay, this describes somehow this state, such states describe uh, Wigner, or not Wigner, through the Wigner function Gaussian states. So like multi-dimensional Gaussian states. And but this is not very interesting if you look at it from the perspective of like measuring uh, position and momentum in that phase space, right? Because yeah, you can sample classically also from the Gaussian distribution. But if you do like photon detection, like you measure the number of photons, then it's not really clear what this distribution is. And it turns out that this distribution is very difficult to generate classically. And we believe, or some people believe, that it can be used for solving really difficult tasks, which are difficult on a classical computer. But not difficult, yeah.
So can we say that this is a subclass of unitaries that can be efficiently described, despite the fact that it is infinite dimensional, that can be efficiently described via this finite dimensional covariance matrices? Yes, and
Yes.
so has a very simple description. This is the only class which has such simple description. Yes, such finite dimensional. Yes, can we say like this?
Yeah, this is like I don't know if I can say that this is like the only class, but this is like a very, how should I put it? It's like a very interesting class of which is quite tractable. So like tractable through these first and second moments. And the statement is also that you can calculate the expectation value of observables efficiently until it is like, I don't know, not too long polynomial in the ladder operators, so to say. So if it's like a fixed length observable in the ladder operators, then you can calculate it efficiently. So that is good at least. But sampling, like particle number detection sampling or photon detection is difficult to simulate. That has only been realized in 2018, 17. So this is like a very new. I mean, what I'm saying is the Gaussian boson sampling is a very new protocol. So it's like it was not always obvious that this might have some applications, I would say. Did I answer your question? Okay. Okay. Then we can go on. We discussed how to decompose symplectic matrices, and now, okay. So I think that we have 15 minutes until the break, until the first break, right? According to the, okay. Okay, so in 15 minutes there will be a coffee break. Until then, I will talk about, or I will start the chapter 3. Phase space formulation. We start by a very simple thing, which is probably, I mean, it is very useful in the derivations of this phase space formulation, because the phase space formulation uses this displacement gate many times. So it's like ubiquitous in the phase space formalism, and we will rename this displacement operator to be the while operator. But I mean, it is usually called a while operator in this context. So I will rename it. And it is interesting because it is the thing that the coherent states are the eigenvectors of the NIL. So in this equation, so if we consider this equation, sorry. So if you look at coherent states, so it is kind of important that if you look at coherent states, this is what I wanted to say, then we can see that the coherent states are the eigenvectors of the annihilation operator, and this we can show by inserting the basically, what do we do here? So you insert the identity, yes, and yeah, okay. So this is here, and you use the, of course, thank you. So and you use this relation which we have already derived and used also yesterday, and from this it is like very immediate to show that this is indeed the case. This one, and from this property, it is quite clear, or I mean, not quite clear, but if you use the relation like this property of the annihilation operator that is this, you also need to use this one, and this is not n-1, this is just n, right? I hope so. Yes. Okay. You can derive some recursion formulas, and from that recursion formulas you can derive the coefficients of the coherent states, which we have not derived earlier, and you can see that we recover the expectation value, or I mean the probability of detecting zero in a coherent state. So we had some similar formula like this, right? So this is very good, and but I don't want to derive it now. So it's yeah, it's a bit involved, and um, yes, this is another thing um, which can be derived by similar formulas. The statement is that these while operators, I mean displacement operator, so this displacement gate, commute up to a phase. Or not, oh sorry, this is not that property. Sorry, they can be merged, or they have this group structure that if you have alpha beta, then you can just insert alpha plus beta into a single displacement gate or while operator, but a phase comes out. And this is important because if we want to show that the coherent states are not orthogonal, then we have to use this identity. So this can be shown by looking at the like an overlap of coherent states. So you have like a beta coherent state and an alpha coherent state, and you can see that if you insert the definition of the coherent state with the displacement gates, then you will have this term, and this is something like this overlap. We could merge the alpha and beta into a single displacement gate, and you will have this formula, which is quite ugly, but this is uh, not the Kronecker delta. I mean, if it would be, or if the coherent states would form an orthogonal basis somehow in some space, or in the Fock space, then this would be like a Kronecker delta, but it isn't. And we expect this because the Fock space has like a countable dimension. So yeah. Okay. So this shows that the if the um how should I put it? If the set of coherent states are complete, then they must be over complete, meaning that the two coherent states overlap. Okay. And how to continue from this? What did I want to tell next? Yeah, I wanted to tell that, okay, so we have this thing that the coherent states are not orthogonal, but they still do resolve the identity operator on the Fock space, which is very useful. So why do they how to derive this? You can derive this by I mean it's like proof outline. We can start from this equation, and we can write the coefficients which we have discussed earlier of the coherent states like this. Although I won't derive it. You can insert the sum. You have two sums here, and the two sums and the integral can be exchanged. And then you will have some integral inside, right? And you perform that integral. And if you do perform that integral, then you will get something like this. Which is the identity. Okay. So, but this is like the first appearance of an integral, is phase space integral. I should also mention what do I mean by this. So like we have this. By this I mean, so alpha is a complex value, a complex variable. By this I mean the real value of alpha, so d of real value of alpha and d of imaginary value of alpha. So if, I don't know, you would do something like x plus I epsilon, then this would be dx dy, and you could convert it into a integral over the R squared plane. Question?
Yeah, so okay, so since you mentioned it, so what is the measure of it? Like, is it
What is the
what is the measure here?
Oh, like the standard measure, like standard, yeah. How is it called? Lebesgue measure, Lebesgue-Stiel's measure, or what is it called? So it is like the, yeah. There is no funny thing going on. So this can be written as like a Riemann integral.
Okay.
So if you want to write this, okay, so this could be written as like, of course, I mean, okay, so you don't do this over the uh, yeah, over functions, but you do this over vectors, right? But you understand is that you do the integral over the um, yeah. So you can rewrite it like this, basically. And there is no funny business, there is no determinant of Jacobian or anything coming out here, right? So this can be thought of as like a summation, basically, over the R squared. And this we call like a phase space integral. So if we go um, over all possible alphas with the coherent states, and we integrate, then this is called a phase space integral. And the space on which the alphas live, basically, that is called the phase space. Okay.
Maybe because the confusion comes from the fact that this is integral of operators, yes, in fact. So the value of this integral lives some operator space, but it is parametrized, yes, by complex numbers. So
Well,
so
yes, sorry.
so it's the region of integration is the complex plane, yes, but the
Ye-
value of the integral is in the operator space.
Yes. So, but you can define analogously. So as for you, what would you do in like see if you would define an integral over a vector. So you integrate each of their variables or each of so not the variables, the vector elements, right, independently. And you could also do it here, but it's like an infinite dimensional vector. That's that might be problematic, and there might be mathematical issues around this, but there isn't. That's the statement. Is this okay? I mean, yeah, so if we want to do it mathematically rigorously, then we would sit here all week. That's the thing. But yeah. So, but you don't have to like perform all these integrals. So generally, people, no one does that. That okay, you look at the. I mean, now we did that, but mm, it's not a. We don't have to like expand it into like in the Fock basis and do this integral generally. We did it now basically. So and it worked. Is it okay or kind of okay? You can look at the derivation in the lecture notes, and it becomes a bit clearer, I think. Okay, is there any more question regarding this? So, okay, this is very interesting because that means that if we want to write the trace of an operator, then we can write it as so trace of O. So let me take an O operator. And okay, let it be trace class, meaning that it has a trace. Then we can write it as sum of n equals to 0 to infinity, n O n. Okay, right. This is this sum. But the statement is that you can also rewrite it. I mean, if we exchange this summation into this integral by inserting an identity, basically, that we can do, you can rewrite it as this integral. Okay. And this quantity, and okay, we have d squared alpha here. Sorry, I just want to look at the lecture notes quickly. Sorry, did I send the lecture notes? Okay, that's good. Sorry? Yes. It has number 3. Okay. It's in the co. I forgot to mention it. Yeah, so I updated it. So it's almost final version. Okay, and it is already 10. So we discussed that we could have like a coffee break, I think, because it is like, yeah. The next one is a bit more difficult. Let's have a coffee break. Okay. So let me return to this phase space formulation of quantum optics. So as we have seen, what we have seen here is that the coherent states have this very nice property that they resolve the identity. This is very useful for rewriting traces, for example, as phase space integrals, as this one. Like this is like a key thing here, that the trace of this can be rewritten as this, right? And okay, so why is this useful? This is useful because, as you have seen, for Gaussian states, it is very difficult. I mean, we didn't really specify how to calculate these quantities. So like, these are very hard to analytically compute. So for example, for squeeze states, I don't even provide the formula. For coherent states, I have shown the formula. Okay, sorry. It is ugly. So you don't want to deal with this. Okay, it's not that ugly. But if you would consider it for like a generic Gaussian state, it would be ugly. If you would also include interferometers, like any generic multimode state, it would be ugly. And that's why if you want to calculate this, you don't want to evaluate these things here, these matrix elements of the operator O. This is in general difficult. However, you can more easily calculate these ones. These not elements. This is a function, or even a distribution in general. So this is easier in some sense to analytically compute for like Gaussian objects and even for Fock basis states. And we will do this later. Okay. So this is very good. This is very insightful at this point. And all I wanted to show, I mean, I wanted to show that if we consider this displacement or displacement gate or while operator, as it is sometimes called, you can. This is like a single mode thing at this point, but you can consider a multimode version. And I will, so it will be apparent when I consider the multimode version, I will write an underline under the alpha. And this is defined by this one here. So I apply the alpha I displacement on the ith mode, right? So this is like a very obvious generalization of this displacement operator. This constitutes, or this is like a corresponds to a layer of displacement gates in your photonic circuit. Okay, and you can see also that if you have like maybe this relation is not that important. I will return to it if it's needed. Yes. Any questions regarding this, by the way? If you don't have any, let's return. Okay. So this is a very interesting thing. We won't necessarily use this, um, but this might be important. Well, this might be important, and it is also very insightful. So this statement says that if we have this displacement operator, and if we take the trace of this displacement operator, right, then the trace is almost almost every time it is 0, except for the case when alpha is 0, because when alpha is 0, then it will not even be a like function, or I mean it is not even, it's infinity, right? So this is like a Dirac delta distribution. Of course, because if you take the d alpha with alpha equal to 0, then you will basically get an identity. And okay, so you can say that, okay, so the trace of this identity is like, okay, it's infinity basically. And that's what is encapsulated here, roughly. So it's like, of course, there is a pi factor coming in. The statement is that you can calculate this by expanding the alpha in the, I believe it is calculated by expanding into the Fock basis. So like this coefficient. Sorry. No. We didn't expand this. How to prove this? Oh yes, with the phase space integral. Sorry. Exactly. That's the, yes. So what you do is to do, and you do it with a beta. Sorry. Yes. Beta, and this is an alpha here. Sorry. Now let me delete this because it's not nice.
And this is the formula for the trace, right? Not for the D.
Yeah, sorry. The trace of it.
Good.
We want to calculate the trace of this. So the trace of this, with the previous statement is that it would be this formula, but you can exchange the finite or like the countable sum into an integral. And immediately here you use this. So yeah, that's why we talked about this. And this can be evaluated. How to evaluate this? Roughly what you would do is that you can write this one as like, note that this is a minus sign here because we apply it on the left. So on the bra vector. Right? We can use this one, and we can also merge these. So for example, there was this relation that this is d alpha plus d plus beta times some phase. I don't write it down. Okay. So and you can merge these variables together, right? And you will have some function which is like the function of alpha and beta. And you can do this integral. This will be like a Gaussian, or not Gaussian integral, but this will be like a very easy integral. And from that integral, you will see that it is it is the Dirac delta function if you perform this integral. Okay. So, but this is like a very interesting thing. And from that, essentially, so if you consider like two of these displacement operators, then you could show some kind of orthogonality of the displacement operators or the while operators with respect to the Hilbert-Schmidt norm in the operator space, like in the so in the space of operators over the Fock space, right? So you could also show something like this means that if you have like d alpha d and this is minus alpha d beta, right? That is roughly d beta minus alpha. So if alpha and beta is the same, then you will get a blow up, an infinity. Otherwise, you get a zero. And this is like roughly like I'm just giving you the idea, roughly an orthogonality. Of course, there is this pi factor here, but we can renormalize with that, right? Okay, so and this gives the idea that maybe instead of using coherent states, which are which are orthogonal or which are not orthogonal, and it forms an over complete basis, maybe we can use the displacement operators in such integral, in such phase space integral. And let me check. Do I have more? No, I don't have more. Okay, so what I wanted to say is that we can write, for example, I mean, I won't derive this, but just to show an example how to write some operator in the phase space integral with not the coherent state, but with the displacement operator or the while operator. You can write it as this one. Yes, and you have this the gamma here. Gamma is another phase space variable. You can write it as this. So this is like a weighted sum of or weighted integral of the displacement operators. And if you perform this integral, then you will recover the vacuum. This is like a very interesting way to represent the vacuum. But we can say something more general, which is like a theorem, the Fourier-Weil relation, which says that if we have any operator, then we can write it as 1 over pi. we are still in single mode Fock space. The trace of d alpha O. Okay. Stop me if you have any question, by the way. And that's it, right? Yes. Okay. What does this mean? This means that you have any operator, you can rewrite it or you can decompose it into a weighted sum over integral of the displacement operators. Okay, so in this sense, the displacement operators are the elementary operators on the phase space. And this is like very powerful. Okay. Even squeezing. So even if you take the squeezing operator, you can rewrite it like this. Interesting, right? But you will have like a very non-trivial function here. So you need to determine this function. Sometimes it is easy, sometimes it is not easy. Um, for squeezing, I think it should be easy. I don't know. Yeah, let me think about this. I don't know if it is how feasible it is for the squeezing. But yeah, it's an interesting thing that you pointed out, that you can decompose anything. And this thing we will call, what is my notation? This thing we will call the characteristic function of the operator O, and it is depending on alpha. This is called the characteristic function. Okay. This is the characteristic function. So just to reiterate, you can write any operator. So for example, if you take any state, rho, so like that density operator, rho, then this rho can be written as an integral over the displacement operators, but the displacement operators are weighed by this characteristic function, which is a function of alpha. Okay. What does this mean? This means basically that instead of talking about operators, we can talk about much simpler things, namely characteristic functions, namely these. If you have the characteristic function of something, and it is like a, I don't know, well-behaved characteristic function so that you can perform this integral, you perform this integral and you will get back the operator. And the idea is that to translate everything into this picture with characteristic functions and whatnot, into this phase space picture, and like write the quantities as integrals. So like the aim is, or like the main aim is to, for example, write expectation values or write probabilities as phase space integrals. So the motivation is that if you have like a state, like you have like a density operator rho, and you want to measure or you want to calculate the probability of measuring an occupation number. So measuring it in the state n, like in this state. Then the probability by Born's rule is given by trace rho of n, right? And this is what we want. But this is in general for if you take any Gaussian state, it is a bit difficult. So this is like difficult. And okay, you have already seen that the trace can be rewritten as like a phase space integral. The aim is to rewrite this smartly as some kind of phase space integral, which might be easier. And also not just easier, it's also more insightful in some sense. We will see why it is insightful. So from this phase space formalism, the connection to like graph theory and perfect matchings will become apparent. Is there any question about regarding the plan of what we are trying to do here? Okay.
So this vector of n means just concrete number of photons in given modes, yes?
Yes. That means that the probability of detecting n1 photons in the first mode, n2 photons in the second mode, etc., nd photons in the dth mode. Yes, exactly.
So you are using this phase space picture mostly as a tool for calculating some other operations, but not to define objects, right? Like objects are defined separately, and then you are using this picture to calculate, for example, expected values, right?
Yes. Generally, that's the idea that you have already some operator, and you translate it into this phase space picture, and then you expect that some quantities might be more easily calculable or something like this.
Okay, sure. Thank you.
Yes. Okay. And also it gives many insights. So for example, I didn't talk about it, but for example, the Wigner function, which is like a representation of photonic states. But also you can represent any operators with the Wigner function. Anyway, okay, let's talk first with about these characteristic functions. For example, let's derive the characteristic function of the vacuum state. Let's write an example. So the first example is the characteristic function of the vacuum. The characteristic function of this is like very easy. We have already seen this. So we have already seen this, but I didn't call it the characteristic function. I'm just mentioning it. So this is trace of d alpha 0, 0. But this is exactly 0 d alpha 0. But this is something that we have already calculated, which is e to the minus alpha squared over 2. And this is not a coincidence. We have seen here in this representation, although we didn't know that the vacuum could be written like this, right? And this thing is exactly the this thing here. Okay. Question? Yes.
In this formula, you have d of gamma and e to minus gamma, but you have integration over alpha, or
Oh, yeah. Oh.
Here is alpha, and
Well,
but in the formula above.
yeah, sorry, here,
Yes. No. In the upper formula for
here.
here, yes.
This is a gamma, but
But this is gamma, but integration is this is alpha, yes? Okay.
yeah, sorry. It should be an alpha. Sorry. Right. Yes. Let's use alpha. Okay. But this is clear now, right? So otherwise, if it would be alpha and the other ones would be, then it would be an easy integral. So yes, I meant alpha here. Exactly. Okay. So we have this here, and we could calculate the characteristic function of the vacuum. That's really good. It's really good. And what can we say? So okay, an interesting thing is that, as I have already mentioned, if you have like a Gaussian state, then you can, I mean, what you can do is that uh, you can write it as you can write it as something like maybe U 0 0 U dagger, and U is linear optical. Okay. The question is how to calculate the characteristic function of any Gaussian state. So that is the next thing that we want to do in this formalism. And okay, you can say that then the characteristic function of any Gaussian state can be written as so like example. Yeah, sorry, pure Gaussian state. Maybe I omitted this, but the thing is that if you want to have like a non-pure Gaussian state, then instead of the zeros, you want to include a thermal state. We have discussed this yesterday, that you have to take the beta to the infinity limit and you will get a zero state. Otherwise, you will get a thermal state. Yeah. So Gaussian state, and I want to do it pure, like for pure state, and centralized. Centralized meaning that there is no displacement. So in the Hamiltonian, there is no linear term involved, and you don't need to use any displacement gates to produce this Gaussian state. So only quadratic Hamiltonian, strictly quadratic Hamiltonian. And if you do this, okay, let's do this. Then you can see that the let's call this rho. The characteristic function of this is something like okay, you can calculate this, but it is 0, and you will have U dagger d alpha U. And we are here again. We need to calculate. Okay, so we have come from the this picture that we apply unitary on the state. We come to this picture in this Heisenberg picture when we want to evolve the operator inside this. And to evolve this operator, we have this formula. We can also derive it, but we have this formula that it is transforms easily. So it's like you can describe it with this symplectic transformation, and it is something like d of S alpha brev, and you take the first D element of this. It is derived in the lecture notes. So I'm taking it as like an ingredient here, right? And from this is okay. So you can see that this is still a displacement. So the conjugation by a strictly quadratic Hamiltonian will still produce like a displacement, but it is like a transformed or rotated displacement. That is great. And you can use the similar formula as we have used before. Okay. And from here, you can conclude that, which is a very important thing, which is the fact that if we want to, how should I? If we want to write the characteristic function of this state, then it will be something like e to the minus 1 over 4, and this thing here, this and there is a dagger here. This is a formula. K is like is something like, it comes out of the formula. It is a 1 minus 1 matrix. S is like this matrix which characterizes the time evolution. And alpha brev, I already mentioned that this is like alpha overline or alpha conjugated concatenated. And you can see that in this formula, this is the covariance matrix. So the covariance matrix is appearing, right? So it is apparent that it is like, it looks like this. Okay, covariance matrix, very important, alpha. This is like the final formula. This is very important for all these calculations. What do we learn from this? So we learned from this that, okay, so this is centralized, so there is no displacement or anything, but it only depends on the covariance matrix, right? What does this mean? It only depends on the covariance matrix, but the characteristic function entirely characterizes the density operator itself, or the whole quantum state itself. It means that, I mean, what I have said earlier, but didn't show, that the quantum state or this Gaussian state can be entirely described by only the covariance matrix. In this centralized case, when we don't use first moments, it's for, yeah. So is this clear now? How this works, or like this dependence from the from the characteristic function, you can get back the original operator by this formula. Like how was this? You can get back. Yeah, so in a multimode setting, question?
Yes. So can you explain what's going on in this exponent of this? This
Yes.
k sigma k, this is matrix multiplication, and what about these alphas?
Oh, the alpha is a vector. So like the thing is that the alpha, I mean here if I consider multimode in a multimode setting, everything here is like a vector. Sorry, I didn't write the underscores here. I omit them, but I consider like a multimode Gaussian state, not just a single mode Gaussian state, although it works on single mode. But now I consider multimode setting where you have like a big symplectic matrix and you have these uh, two. This is like uh, length d vector, and this brev is like, it's like it's a 2D length vector, and this is also yeah, a 2D by 2D matrix. And of course, the covariance matrix is also a 2D by 2D matrix.
Yeah.
So this is an inner product, basically. Yes. Um, any more question? So this is a Gaussian function already. This is like the property of like if you have a Gaussian state, then you will have a Gaussian characteristic function. And if you take a Gaussian function as a characteristic function, you can reproduce a Gaussian state from this. So there is this connection. And yesterday you asked why is it Gaussian? This is why it is Gaussian, because it is a Gaussian function.
Okay, but finally, what's the expression in the exponent? So it's some quadratic function of alphas?
Yes,
Okay.
exactly. Okay. Okay. I also want to mention that you can calculate the Wigner. You can calculate anything from the characteristic function, and one thing which is usually calculated is the Wigner function. There are many interesting properties of this Wigner function. We won't detail the most interesting properties, but it is defined like this. If we consider a D-mode system, then you can write it as this phase space integral. This is in some sense a complex version of a Fourier transform, basically. And this is the Fourier transform of the characteristic function. I mean, the characteristic function equally well describes the state, but we tend to use this function sometimes because it has nice properties. So you can recover like position and momentum distributions by taking its marginals. It is almost a distribution. For Gaussian states, it is a distribution, but for general states, it is a quasi-probability distribution. So the statement is it can be normalized. It is not normalized in this form, and it's almost a probability distribution. It is called a quasi-probability distribution. Yes?
Can you repeat just what you said between Wigner function helps to connect the characteristic function with?
So maybe you meant that yeah. So you can equally use the characteristic function and the Wigner function to describe the state. From the Wigner function you can recover the characteristic function, and but so you ask why do we use the Wigner function? We use the Wigner function because of the I didn't write this down in the lecture notes, but if you take the marginals of the Wigner function. They can give the position or momentum distribution. So you can essentially recover the wave function or the wave function amplitude from this Wigner function. But the interesting thing is that this, so in order for, so in order to make quantum mechanics work, it is not a probability distribution in general. It's a quasi-probability distribution. But if you take the marginals, these will become true probability distributions. So yes, nature doesn't require the Wigner function to be positive. So that's it.
Can I have also philosophical question related? So why do people care when there is negative values in the Wigner function? Because I remember from many talks, I mean, not understanding what was going on, that, pointing out that there is something negative in the Wigner function, that was interesting for some reason.
Yeah, it can be said that, okay, so if you have like a fully like positive or non-negative Wigner function, then some things can be simulated more efficiently on a classical computer. Cindy.
Exactly. So if you have a positive Wigner function, then you can uh, do a simulation of a system and the sampling algorithm with homodyne or heterodyne measurement efficiently. And if you have negative regions, you can still do that, and it becomes less and less efficient, so not efficient, if the negative regions are bigger and bigger. So there is this trade-off between, like if you have little negative regions, then you can still do pretty efficient simulation.
Efficiency on classical or quantum machine, you said?
The classical simulation of the quantum process is then not efficient if there are lots of negative regions there.
Yeah. Yeah, so that's why it is like sometimes it is important that the Wigner function must go below 0, but for us it is always positive. Because like as we have said, like the measurement of the position or momentum in the Gaussian in a Gaussian state is like, okay, this has already been said, but the Wigner function, from the Wigner function, because it is like a Gaussian function, you take its marginals, it's still a Gaussian, and you can effectively calculate it on a classical computer. So it is good. If it is like not the case, so if it is not a Gaussian function, then it's not easy. Okay. Is this answer to your question? Okay. Okay. And now I just want to, I don't want to derive this because it's like tedious and we don't have time. But the Wigner function of a Gaussian state, okay, so it is also Gaussian, and this is something like, you can imagine that you have some formula, but the interesting thing is that what is appearing here is exactly um, the inverse of the covariance matrix, like this. Okay. So, okay, and you could say, okay, what if the covariance matrix is not invertible? It must be invertible. So, so due to Heisenberg uncertainty relation. So there are, I mentioned this yesterday also, that there are some constraints on this covariance matrix. Yes. So it has to positive definitive. Okay. So that we know that this is like a Gaussian function, and somehow the covariance or the covariance is indeed given by the covariance matrix. So that's why we call it the covariance matrix when we talked about second moments of Gaussian states. Okay, and you can indeed verify that this is normalized up to a factor of 2 to the power of d. That's it. Okay, that's all I wanted to say about Wigner functions, although they will come up later. And now, quickly, I will talk about the S-ordered characteristic functions. Yes. So why do we care about this? Let me define it first. An S-ordered characteristic function is something like this. The original characteristic function, very good. And also this thing here. Why is it interesting for us? Okay, so this is just a multiplier with the um, ah, it should be a norm because it is like a vector now. Maybe I have missed this also at some point, but yes. Why is it important for us? It is important because if we want to um, calculate different things in different ordering, for example, in normal ordering, then you need to use this modified characteristic function. So what do I talk about? I talk about the following, that if you have like this d alpha, you can, for example, so you remember that you can write it as alpha a dagger minus alpha a bar a, but you can also write it as e to the alpha a dagger e to the minus alpha a plus or times some multiplier, which I didn't derive and I won't derive because it is also tedious and I would have to explain the Baker-Campbell-Hausdorff formula, which I don't want. You get this. And this is very interesting because if you take the alpha, and for example, let's say that I want to take the derivative of this operator n times, right? And then you evaluate it at alpha equal to 0, then you will get minus 1 over n a to the power of n. Why is it the case or why is it interesting? So, sorry, now it is true. Or let me write it. Or maybe it is simpler if I write it without.
Wait, but you have the underscores and overlines.
A dagger. Yes, the
complex conjugate.
Okay, so
that is complex conjugation. Okay. So you are asking about what does the derivation rules. Okay. So this is like non-trivial. You have not encountered before like this derivation by a complex variable or something like this.
no, I'm just, the dumb programmer. I never
Okay.
done complex analysis.
No, it's yeah. So the thing is, okay, I don't want to give the definition, or I mean, I want to give the definition, but it's not like time efficient to. It's not time efficient to define this. But the most important thing is that you can regard alpha and alpha bar as independent variables. That's it. Okay, so if you derive by alpha, then this alpha bar variable will not enter into the game. That's it. So you define it like this. You define this complex differentiation like this. If you are interested, you can search for Wirtinger derivatives. That is the name of this, Wirtinger. Wirtinger with a W.
Funnily enough, this is used in physics all the time without giving the proper definition. Physicists don't give the proper definition.
Yeah. Yeah, so it can be a bit confusing. Yes? 1/2. You mean if you write this Wirtinger derivative as like the it is something like this, right? Ooh. Do you know where this 1/2 is coming from?
I think it's just coming from that you obtain if you would have a pure function of a polynomial of alphas, that you get the same rules as for the
Yeah.
as for the usual um, derivation, I would say.
So with this you can verify that if you differentiate this, then you will get this one. I mean,
And also, if you differentiate alpha bar, you get 0.
yes, that is important. That
Sorry, I didn't understand what you said on the 1/2 again.
So actually, check what Zoli is writing. You have to have that 1/2 to get that formal rule that looks like derivative with respect. Formally, it's the same as the derivative with respect to like a real variable.
It's just related to this simple stuff.
Yeah.
Because the consequences in physics are huge, actually. Okay.
the consequences of in physics or what
Yeah.
and this appears many places, yeah. But this is like a yeah convenience thing. So you can also do it with real values, of course. But this is
So I have to find a physical argument for that. Okay. Thank you.
this is just a convenient change of variables. So okay, okay. So and this is interesting. Why is it interesting? Because or like this thing is what it means that it is like the generating function of the ladder operators. And this is very powerful because, for example, if you want to calculate, like, let me simplify this, that if you want to calculate a dagger and am, like this expectation value of this uh, observable, it's not necessarily an observable, but this polynomial, if you want to obtain this, then what you can write is the following, that you differentiate n times by alpha and m times by alpha bar. You include this -1 sign, which is coming from that particular form of the displacement operator, and you will get x rho. Yeah, you want to differentiate x rho 1 alpha when there is no, because I'm doing it for single variable now, and you evaluate it at alpha equal to 0, and that's it. So that's how you can get higher order moments, for example, from Gaussian state. So if you would include the Gaussian state characteristic function here, this is like a Gaussian function, you would differentiate it, and if you differentiate it and evaluate it at alpha equal to 0, then you will get the higher order moments. It's very convenient, I think. This is a thing that you couldn't do, I think, without this phase space formalism or without characteristic functions. And that's where the power of this of the phase space formalism comes from. Okay. Okay. So and a very powerful thing is the following, that if you want to, so as I mentioned, consider Gaussian states. If you want to, how do I put it? Want to calculate the you can calculate the characteristic function of this, which is a Gaussian function. And you know that, okay, in order to obtain higher order moments, you want to differentiate this Gaussian function with, I don't know, with these numbers defined in the exponent of the a dagger and a, right? And then, okay, you will see that the derivatives of the Gaussian functions have a particularly nice formula. And the statement is, it can be a proposition, although it is a very important proposition which we can use later, that if you take the derivative of this Gaussian function, and I'm considering now multivariable derivative. So like you understand, this is like this composition of the differentials with each variable. So like x is some, I don't know, is like variable of vector of n independent variables, for example. And if you want to differentiate this thing, this e to the 1/2 x transposed sigma x, these are all vectors, then you will get some very interesting quantity. Of course, you evaluate it at 0, which I have not written down in the lecture notes, but you evaluate it at 0. You will get the following quantity, which is some, this is the first time it is appearing, but it will appear multiple times. I will write down the formula and I will explain what these are, or what this is. Sigma ij. Okay, where PM, question?
Yeah, you have the derivative to the power of n sub, and now I'm lost once again.
Sorry,
N and powered of vector.
so n is also a vector of n1 nd. Okay, let's make it simpler. Let's make it simpler, because let's don't use this n. Okay.
You mean multimode?
Yeah, that is for, this is multimode, because you have okay, let's use d here just to make it more difficult.
Is this x variable now a real variable?
X is real, but it doesn't really. I mean, you can make it complex as well. You can switch bases and.
So now we abstract from phase space. Yes, this is just mathematical formula.
This is mathematical. So
Okay.
this has nothing to do with phase space for now.
Okay.
Okay. So this has nothing to do with that. Okay. And let's discuss the case where when we have like okay, this derivative, which means that you derive by each variable once. That's it. Okay. And this is this formula. This one. And the PM means the perfect matching, is perfect matchings. And I will define it by an example. So consider like the set, I don't know, let me consider, so for example, 2D, let D equal to 2, then 2D is just 1, 2, 3, and it is a set, so I will use this notation. These four numbers, and the perfect matchings of this then, so this is 4. Then it is 1, 2, and 3, 4. This is one perfect matching. And another perfect matching is, let me go down, 1, 3. You match 1 with 3. and you have 2, 4 left. This is also a perfect matching. And the last perfect matching is 1, 4, and 2, 3. So you can imagine that you have like a graph with 4 vertices, 1, 2, 3, 4, right? And you are trying to match all the edges or all the vertices. Yes, like for example, you have this one, 1, 2, 3, 4. It's this one. You have this matching. Let me use another color. 1, 3, 2, 4. This is this one. And you also have this matching. Okay, it's a very weird picture, but it's this one. Okay. So these are all the perfect matchings. So it becomes a bit clear why is it related to graph theory a bit. Because now I have written like, okay, so this is not okay, this is a graph, but I didn't connect the edges, but you can consider this as like a fully connected graph. Anyway. So you have this formula. And we have a name for that. Or I mean, graph theoreticians gave a name for this. This is called the hafnian of sigma, basically. So this is like the definition, and this is like very, very important. So the hafnian in like quantum optics comes from this kind of derivatives, and these kind of derivatives come from the phase space formulation of quantum optics. That's how you get the hafnian, and there is like no traditional way for obtaining this hafnian, I believe. Okay. Is there any question? So like this is like a very non-quantum optics or non-photonic quantum computing statement.
Just to be clear, when you have like d equal 3, roughly what happens? Do you have only pairs, or do you consider?
Yeah. Oh, okay. So let's discuss the d equals 3. In the d equals 3 case, you will have let me go with the pairings. So you have this pair, and for example, you have this pair. Tell me when to stop. You have this pair. Let's.
Okay, so you basically cover the entire graph with the pairs.
And you have to cover everything.
Yeah, and the requirement is that you do it once and exactly once. So every vertex belongs to exactly one pair.
Yes.
Okay,
yes.
that was missing for me.
Yes. So the intuition behind this is that if you do this differential, right, then because it is like a second order thing, all the like coefficients of the second order terms have to come down in pairs, right? Basically, that's the intuition, and that's why you have like you need to have like perfect matchings. If you would have like a third order, I don't know, polynomial in X here, you would get something different. Okay. So this is I didn't find the derivation of this anywhere basically. Or I mean, there is like a very difficult derivation from a different formula, but I have written down in the lecture notes the derivation of this thing. But it is not hugely important how to derive it exactly. The important thing that this is like the connection of graph theory and quantum optics. Okay. Yes. So okay. So let me write down some other type of quasi probability distributions if there is no question. Now we have like this hafnian, but we don't know how it will appear in the probabilities of detecting certain outcomes from a Gaussian state. So we don't still have the techniques yet, but we obtain the hafnian. Now I want to talk about the P representation and the Q function. Okay, I remember that with Tomek we discussed like 3 or 4 years ago that we need to understand this because it might be important. So now I'm telling it to Tomek so that we both understand. Okay, so we have like S order characteristic function which corresponds to different orders. Okay, so I might elaborate on this a bit. So like we had these characteristic functions, and if S is positive, or like sorry negative, no, positive, then you will get this form of the displacement operator. But you can get like it is very particular that you have in front the A dagger and after that the A. You can do it in the other direction, but you will get a sign difference, and there will be a minus in this S basically. And if you write 0 here, you will get back the original characteristic function, but you don't get like this ordering that A dagger is front and A is on the back, or A is in the front and A dagger is in the back, but it is like a symmetric ordering in the S equals 0 case. Not hugely important for us. But yes, but just remember that these were these modified characteristic functions, and from these modified, sorry that I have to go back, from these modified characteristic functions, what you can say is that you can define alternative Wigner functions, so to say Wigner functions, uh, which on a single mode they look like this, just to simplify the discussion. Again, you have this Fourier transformation kind of thing.
What is the origin of this phase term? Why is it exactly like this?
This thing.
Mm-hmm.
Okay, so how to put it? It is there is a different form of it which closely resembles to like the coefficient in the Fourier transformation. So if you do the Fourier transformation fk, then you have, I don't know if up to normalization, but e to the I k x fx dx, and this is like analogous, like similar. Okay, and that's why I call it a Fourier transformation. It is analogous to that. Okay, so I put this here. Okay, so this is like the S-ordered Wigner function. But these have proper names, these Wigner functions. And the one thing is that in the S equals 0 case, you will get the Wigner function, the original Wigner function. So like um, the S equal to 1 case, you will recover the P function. and the s equal to -1 case, you will recover something called a Q function. And we will use both the P function and both the Q function. And what is the statement? There is like a statement regarding the P representation, like a very famous theorem, that I mentioned that the displacement operator is nice because you can write every operator in the displacement operator basis, so to say. But this is also true for coherent states. So you can write, and this is like this is uses the P representation. This goes as follows. With the P function, d alpha. Where the P rho alpha is W plus 1. So this is like the Wigner function corresponding to the +1 ordering rho alpha. Okay, so you can write also this integral. This is very interesting. This can be derived, but it is like, yeah, it's a bit tedious and also uses the like previous derivations with the displacement operator, very analogous. And we can also say that this is one thing, and the second thing is that the Q function can be written as something like, so in a single mode at least, it can be written as this one. So everything is single mode here. On multiple modes, you insert vectors here, and wherever you see a pi, you take its dth power, basically. Right? Okay. And there is like a statement. It's like the final statement which I want to say now. Or maybe not the final. Anyway. But there are two statements. We want to calculate the it's a proposition, the P function of something, and we want to calculate the Q function of something. The statement is that the P function of Fock basis states is something like this. And I should mention that this is not a function. I mean, you will see. Yes. And you differentiate the Dirac deltas. And I should probably stop here and explain what I do mean here. Or what do I mean here? Can you guess what I mean here?
I mean, step function, like, like in electronics, that differentiation over Dirac delta is a step function. And actually, you should, of course, go through the theory of distributions, etc. But it does it.
It's the integral, no?
Pardon?
Did you mean that's the integral?
Yeah, okay, yeah, that's true.
That's the integral.
Sorry, no, yeah, that's integral.
So yeah, it's.
I mean, you have to go to something that makes sense. It doesn't make sense, of course, here.
It doesn't make sense. In this context, it doesn't make sense. So whenever we talk about distributions, it's like it's not that you can evaluate this or something. It only makes sense in a certain context. As for the Dirac delta, so the Dirac delta is not a function. let me explain it. So the Dirac delta, if you integrate the Dirac delta with some function, right? And you say that, okay, it's like x minus, let me write it like this. X minus a f x dx, you will get fa. This is like, this could be viewed as the defining relation for the Dirac delta. This is what we want from a Dirac delta. Okay. And what do we mean when we differentiate? So when we differentiate, what we will get, if we want to evaluate this one, x minus a fx dx, then you can rewrite it by the chain rule to minus this one. You remember the chain rule for integrals, right? So I mean I'm talking roughly here. So it's like it what does it mean to integrate a distribution or whatnot? But the thing is that we can use the chain rule here. So we have this. We can put the derivative from the first function to the second function, right? And there is like if you use a chain rule, there will be a term where no derivatives appear, but is evaluated. I mean, if you consider like such function which is like a decaying function, which we always consider like it should be like some Schwarz function, Schwarz distribution. Then anyway, I didn't say anything. So if it's like a smoothly decaying function, then this would be true. And even also for this one. Then you would get the differential of x at a according to this formula. So like this is like the this still holds here, right? And you have a minus. You have a minus. I forget it. Is this kind of okay? It's yeah. One should take like a yeah, like a functional analysis or something course to properly understand this, because it's like many things are not very well defined, and it's everything is very physicsy now. So but anyway, I think this can be found. So if one searches for like Dirac delta and distributions and weak derivative, then you would find it. Okay, so this is like this. We don't know how to interpret this, but if it appears in a phase space integral, we can probably evaluate it. That's the point. I'm not planning to derive this. I mean, the derivation is in the lecture notes. We said that when does this stop, this lecture? So it stopped 5 minutes ago, right? Yeah, one more proposition, which is like but this is like a proposition which we would expect. This is like the last thing. Q function of Gaussian states. And here I mean pure and centralized. to simplify the discussion, because if we don't do this, then it will not be simple. And the statement is as follows: that okay, you expect it that this will be a Gaussian function, and I will write it down because this will appear in the derivation of GBS, or like the probability distributions in GBS. So this is a multimode formula. And now I didn't explain what sigma is, but I will. There is a dagger here, where the sigma is something called by the way, it's called the Hushimi or Husimi, I don't know, I call it Hushimi Q function. Oh no, Q matrix. Sorry, this is the Q matrix. Q matrix of the Gaussian state. Okay, so you add just identity here and you divide it by 2, and that's it. And this will appear in the formula of the probability distributions, this exact Q matrix. Okay, I don't plan to derive it, but you can derive it from the characteristic function as before, or as like the regular Wigner function, but you have like an extra term coming from the modified S-ordered characteristic function. But you essentially have the same integral, you just have to do this Gaussian integral, and you will get it. Okay, and that's it for today. Is there any question? Or before lunch, that's it for before lunch. Okay. If there is no question, we can go to lunch or something. Okay. Thank you so much. Okay, then I repeat that we do now the exercises of the um, morning lessons or morning lectures, which are about the phase space formalism of quantum optics. And the first exercise is, well, it's yeah, I didn't write down what is equation 3.4 here, but equation 3.4 is the expression for the coherent states in the Fock basis. So that's the exercise. So it says that we have to prove this equation. If I remember correctly, it is something like this. I've used it a lot, unfortunately. So we have to prove this. This is a formula for the, so this is the formula for the for the coherent state in the Fock spaces. How do we prove this? There is a hint written which uses the fact, so there is one way which you could use the fact that the so that this is like the eigenvector of the annihilation operator with eigenvalue alpha. There is one way, but there is also another way to think about it, which might be a bit more easy. So in order to do this, you need to write alpha as some kind of sum of coefficients, or yeah, with some coefficients in the Fock basis, and you will have like a relation for the Cn, which is determined by this equation, and it comes out what the Cn is, essentially. The second way, which is maybe a bit better, I think, is to use the following, which we have already done in the lectures, is to write this as d alpha of applied on the vacuum state, right? And d alpha we could write as e to the alpha bar a dagger e to the minus alpha a. And there is this term which is e to the minus, I think it should be this one, if I remember correctly. Right? We can use this one, this formula. And this is also very easy because now you will have, so if you want to write d alpha applied to 0, this will be this one thing. Oh, sorry. Let me just write the phase in front. So this thing can be moved in the front because it is just a phase. So not a phase, sorry, just a multiplier, not a phase. Sorry, it's a multiplier. And we have this term here, this term here, applied to 0. But we know, of course, that the well, we can use the fact that how do I, yes, we can use the fact here that the a applied to 0 is 0, of course. So that this exponential, e to the alpha minus alpha a applied to the 0 is also just 0. The 0 vector, or like the vacuum state. Because if you expand this exponential, then there will be an identity term. And that will yield this remaining vacuum. So we will have e to the minus alpha squared divided by 2, e to the power of this thing here, 0. Okay? And now, what we want to calculate is this thing. We want to expand this. Let's expand this. It is expanded like this. A dagger to the power of n divided by n factorial, I believe. Right. So, and we know that, and also we know that I put it here in a cloud, that a dagger n, as we have learned it, divided by square root of n factorial, applied to the 0, is n. Right? So, this will lead a square root of n factorial if we apply to the vacuum state. So we can further write that this is this thing here. Sum n equal to 0 to infinity. There is a conjugation. Maybe there was a typo in this formula, right? There should be, because the conjugation should be in the other term. Sorry about this. I hope that I didn't mess it up in the lecture note. Yes. So we have this alpha to the power of n, square root of n factorial, and we get an n here by inserting this formula in the cloud. Was this clear? Is there any question? Okay. So this didn't use any characteristic function or p function or q function or Wigner function or anything. This is just like a very basic derivation. Okay. Okay, second exercise. Plot the Wigner function of a single mode vacuum state in Picasso. That we can do, definitely. However, what I would like to do is to do it online, because we have like an online simulator, which also uses Picasso, and we can display Wigner functions there. Although we can also display Wigner functions in the in a script using matplotlib, but I think it is more convenient now, also due to time constraints, to do this online. So we have this website. We can go to the simulator. So I'm just showing it to you because maybe it is easier to visualize it like this. Yeah, so we want to start from a vacuum. Well, it's not necessary. I mean, we will have to show a coherent state anyway, so that corresponds to a coherent state with zero displacement. That is okay, I think. So I execute this code, and there is like a visualization of the Wigner function right here. I don't know if you can see it. So this is just a peak. This is like a Gaussian peak, right? And we can do some funny things here. You can see that it is centered around at 0, 0, but I can displace it. So I can just say that, okay, I will displace it by 3 or something. And I can also specify some angle. I don't know, pi over 3. And it will displace it accordingly. You see that the peak of this is now somewhere else, right? So it's okay. So the problem is that the this function or like this graph is always centered. So you don't see it, but you can see it in the axis. The more interesting thing is that when you do squeezing, for example, when you do squeezing, then the shape of it also changes. So for example, let's squeeze with 1. That is a big squeezing. And if I run it, then what will happen? Do something. Ah, yes. So you can see that this is like a peak still, but it's more like a sword or something, right? So it is squeezed along a direction, squeezed along the x direction, and become wider in the p direction or in the momentum direction. Here you don't see it because you see that it is smaller, but the scale changed, uh, so that the Heisenberg uncertainty is still preserved. Okay, so previously the scale was like I don't know, 10, and here you can see 40. So it's like it became wider in the p direction, right? And also you can see the probability distribution plotted out, and you can see like some example code or like the code which executes this circuit. Anyway,
Excuse me, this probability distribution is in which coordinates?
oh, this is in the phase space.
Yes.
So in the upper one, ah, yeah, the particle number detection probabilities. Yeah. So yeah, it's like it's a 2-mode setup now. So I embedded in a 2-mode setup now. So that's why the 0, 1 probability and all these probabilities are 0. But you was, yeah, it's logical, right? Or
So these are probabilities of detection, like 3 particles in first mode and 0 in other, or
so this is 0 particle in first mode and 0 particle in second mode. This is 1 particle in first mode and 0 particle in second mode. This is 2 particle in first mode, 0 particle in second mode. But so the problem is that okay, so I have 2 modes here. I don't know how to delete 1 mode right now, but I don't know if I would apply something else here. I don't know, like also a squeezing, then I would have probabilities also there. Yeah. Okay.
But then the Wigner functions are independent, as I can see.
Yeah, the Wigner functions are independent.
And what happens if you have some kind of interaction between modes?
Interaction between modes, then you will have like you mean that that you have like a interaction between modes, and then you take the Wigner function of a single mode, right? Then you will still have, surprisingly, you will still have a Gaussian state, and you will still have a Gaussian Wigner function. So like that is a fact that if you have like a Gaussian state on D modes and you throw out however many modes in your system, you discard them. You don't care about these. Then your remaining state is still a Gaussian state, although it is mixed in general. But that is also expected.
Yeah, okay. So in a sense, that's not equivalent to like how block spheres behave in like for qubits.
That's not
Okay. That's not a good analog.
this is a different picture. That is not a good analog, yeah, because you don't have the block sphere here. You have so like the equivalent of block sphere here is the Wigner function. Or like not equivalent, but you know the visualization of the qubit is like the block sphere, and the visualization of like Gaussian states is this, or like any photonic quantum state is this. That is what we have instead of block sphere. So that is the only connection.
Yeah, but from Wigner functions of particular modes, you cannot reconstruct the Wigner function or the state of the combined modes. Is it true or not?
Okay, so if you have this is getting deeper. So if you have like subsystems, and on each subsystem you have Gaussian states, it can be I don't know, either mixed or pure Gaussian states. Then you can construct the Gaussian state, the big Gaussian states from them if you do it in the Fock space picture, by the tensor product. If you do it in the covariance matrix picture, you just stack the covariance matrices together by a direct sum. Basically, that's the thing. But you don't necessarily get a pure Gaussian state in the end, and that is called something like the marginal problem. That is there like a pure Gaussians? Is there like so it's not necessarily restricted to Gaussians. Is there a pure state uh, which you can like trace out all the subsystems, and you will get those prescribed states which you have on your subsystems, right? So,
But no, okay, so the question was basically, so there is not enough information in Wigner functions of particular modes in general to reconstruct the, let's say, Wigner function or whatever image of the composite system.
there is because you just multiply them. So like what you so if you do tensor product between states, then this tensor product will translate to a multiplication in terms of Wigner functions.
Yeah, okay, but but assuming that you have entangled states, entangled modes,
okay,
then I understand that it's not feasible, or is it? Entangled Gaussian modes.
You have two entangled Gaussian modes, and on each Gaussian mode you have some kind of prescribed state. Or is it what
Yeah, I mean, what happens then if you have entanglement to Gaussian states? So is it like, is the marginalization tracing out of one is still Gaussian, but doesn't carry all the information? I mean, the traces do not carry enough information to reconstruct the original Gaussian, or do they carry?
So I
The
mean,
partial traces.
I see what. Okay. I think I understand what you were saying. That okay. So consider this: that you have like there is no space left. Or I mean, I can make another page. Okay. So if you have like a big Gaussian like you have subsystem A and subsystem B, and you have like a covariance matrix. Let's write this covariance matrix as this, and you can write it as something A, B, B, and you will have something also here, A, B, and B, A. But it is symmetric, so B, A is also A, B transpose or dagger. Yeah, so you have this. If you trace out, so if you take, so for example, if you want to look at the covariance matrix on the subsystem A, then this will be, I mean, what I denoted by sigma AA, right? That's the thing. If you do it for B, you will get similar. So if you trace out, you will only get these, but this will be discarded. And this is still like part of the original Gaussian state. So you cannot recover. You can recover some Gaussian function or some Gaussian state, but not the original. You can recover multiple ones, by the way, as it is apparent now. So you can, I mean, there is like some restriction on what to put here in the off diagonals, but you can put zeros here, or you can put, I don't know, anything which yields like a proper, yeah, Gaussian or a covariance matrix, which fulfills the Robertson-Schrödinger uncertainty relation, which is like the quantum optics counterpart of the Heisenberg uncertainty.
Okay, so that basically responds to my question. Thanks.
You're welcome. Okay, so that is that. So I have shown this. Okay, you have these Gaussian functions. Uh, what else? So I can also.
I have a question because I'm running the same simulation, and I see the R parameter is 1, yes?
R parameter. Yes, yes.
Squeezing. Ah, okay. And
I think.
I see a bit different photon number distribution. I don't know why.
Do you use the Gaussian simulator?
Yes, Gaussian simulator.
And you have a very different.
Yeah, but maybe the
But
normal.
these are very small. So like these are very, very small. So if you, okay, you might be seeing a different thing because of numerical inaccuracy. Could it be possible? So if you use a squeezing of one, that is too much, and well, this is like a displacement of 3. So if I decrease it, these values might not be that small. So you can see on the graph. Ah, okay. So these are like normal values.
Oh yes.
So if you have only yeah, you don't include the squeezing and you only have displacement,
Yes.
then you will have this kind of probability distribution.
Yeah. What was the difference? What's
The displacement. So I displaced it by some amount.
Aha.
So I don't know. I displaced it by 3, which is a huge amount, but like 0.5 is like very conservative, and this way you get like a different probability distribution.
Zasłania, dla tych parametrów. Set displacement robisz jakiś tam, powiedzmy, że 1. To masz liczbę, a tam poszło numeryczne.
Okay. Okay.
Okay. If we want to numerically obtain it, we can also do this in the Picasso, like the Python interface. So there are methods for that. Anyway, okay. So this is good. Is there any question? Yeah. Do you want to see how it looks like if there is like a nonlinearity when it goes to negative?
Yeah.
I can also show it to you.
Sure.
Okay, new project. Let's let's do this. I don't know. Let's call it new project. That is good. Okay. Maybe sit down because it's easier. You want to prepare something in the Sorry? It's pure Fock, but you can choose whatever other than Gaussian. The Gaussian is like restricted because you don't have nonlinear gates.
Ja nie widzę, do którego operatora
Yes.
to jest.
So I have a vacuum here, and I include some squeezing.
No.
You need to create particles, so you can pump particles into the system by including a squeezing, and you can also simulate this, and you will get okay. It is getting funny because okay, you will have these problematic points here. This is not the same Gaussian as you have seen before, but this is because of the cutoff. So because we are simulating in the Fock basis, we don't include all the terms from the Fock basis. But if we include like a higher cutoff, then it is disappearing, right? So it will approximate the Gaussian distribution more, well, or better, yes. And if we want to include some nonlinearity, then I know what to do. So one can do this Kerr gate, which simulates the Kerr effect. And this Kerr gate, I don't know, I specify what usually works. I think 1.0 usually works. And you will have this kind of function. And you can also see that it goes to negative here. Now it is definitely negative. And this is like an interesting Wigner function, which is not a probability distribution anymore.
Więc file new, tutaj wybierasz project i podasz na inną. Full focus.
Dobra.
Yeah. Cool.
Dobra.
Is this okay? There any questions? You can also plot these in the Python interface as well. If you want, there are functions for that. Just make sure that you install matplotlib.
Że taki na pewno.
No.
Aczkolwiek nie wiem co oglądam. No nie rozumiem,
Okay.
co powiedzieć. Ma intuicji żadnej.
So I think we have done many of these exercises. So we have done this, this, and this. Now we have to calculate. Yes. So we need to calculate the Q function of a single mode coherent state. I will do this. I will do this here. So how to do this is the following. We have to remember that the Q function is something like this. And we want to calculate the Q function of a coherent state with parameter beta, for example, is nothing else than the -1 ordered Wigner function or quasi-probability distribution of this thing, right? With the same parameter. There is no underline because it's single mode now. But we also know that you can also calculate this directly, and you have to perform an integral, but there is a shortcut, and this shortcut says that you should just calculate. So then there was a row here, which is like the density matrix, but we can input it here in this formula. I will remind you what it was. So in this formula, it's this. Originally, it was 1 over pi alpha rho alpha. Okay. So we're using this here. So this is nothing else than the 1 over pi of oof, uh, 1 over pi of this thing here. But okay, we didn't actually calculate this one, but we have shown it in the it is in the lecture notes, and we have I might not have written it down. It's in the other script here, yes. Where is it? Not this one, not this one, but this one. Yeah, here we have the overlap. I won't copy it now. I mean, it's unnecessary, but you can see that it is some function of alpha and beta, and you can imagine it, that you can just input this function there, and there you have it. That's the Q function. It's very, yeah, it's quite easy. Okay, and we won't go through this again. Okay, and now, is there any question regarding this? Like,
Thank you.
yeah?
Can we do it in this Picasso simulator? This display PRQ function instead of Wigner function or not?
Not yet. Not yet. I mean, but you can plot the Q function, but not plot the Wigner function, but not the Q function. Also, you can calculate the Q function, or Q matrix. Sorry, the Q matrix you can calculate. There is like a method for that in Gaussian state, which, yeah, if you know the formula for the Gaussian state Q function, then you can just input that and that's it. Mm. Yeah, but it is similar. So it is like a similar Gaussian function as the Wigner function. Um, yes. And also I don't, yeah. Yeah, so this Q function is like, it is really a function. I mean that it is not some messed up function like the P function usually is. So this Q function, technically we can plot it, I think, in most cases. The P function, however, is, I mean, it's possible for Gaussian states, but for like a Fock state, you have seen that this is like a derivative of a Dirac delta, so it's not possible there. Okay, that was just a comment. Okay, okay, next exercise. Okay, no, I want this one. Okay, so we have finished with the Q function of a single mode coherent state. Now we calculate the P function of the single mode coherent state. This P function is a bit more difficult. So P function of single mode coherent state. Okay, that requires some calculation. So what do we have to do first? We have to calculate what are the steps. Like the first step is to obtain, if we have not obtained it, the characteristic function. The second step is to multiply with I believe, this thing here come from the ordering. Okay. And then we can calculate the this Fourier transform, which I have mentioned. Yeah, this will be a function of beta. Oh, and there will be many of these displacement parameters here. This will be a bit confusing. And then you calculate this integral. So you have this e to the beta gamma minus beta gamma, right? And then you have this +1 ordered characteristic function. And this is the p function. Okay, this is a bit more difficult. So what is the characteristic function? The characteristic, let me make another. The characteristic function is as follows. We need to calculate the overlap of, for example, this state by this displacement operator, right? This is very good. This is nothing else than, by the way, so alpha d beta alpha, right? This is, by the way, nothing else than the q function, or pi times the q function of the displacement operator of beta, the variable alpha. But we have a formula for this. I mean, what we did is that already in the lecture note, and I already mentioned this, that you can essentially evaluate this by using this formula for the product of displacement operators. So we have already seen that we have this multiplicative property, right? And also you can find it in the lecture note, I think. Or let's find it in the lecture note, because it has already been evaluated somewhere, and I don't want to. Yeah, this is a general case. I don't know if it is the it is, this is the one. This is the one. Okay, I need this one. I will copy it. I mean, we didn't go through this derivation. Oh yes, this can be done by noticing that this. I will do this because yes. So we can also see this. Let's not do this way because it is a bit more involved. I mean, okay. We can notice that the beta is nothing else than e to the beta a dagger, e to the minus beta conjugate a, and there is this this phase factor here, right? And then what we can do is to rewrite this as e to the minus beta squared divided by 2, and then we have this thing here, this e to the beta a dagger and e to the minus beta a alpha. And we notice that, okay, so the operator A has so the eigenvector of A is alpha, or one eigenvector of A is alpha with eigenvalue alpha. And we can further write it as, so this is becoming e to the minus beta alpha, and alpha stays. And this one is becoming similarly alpha stays and e to the beta alpha, right? This is kind of okay. I think it is okay now because the A dagger is acting on the bra vector, so that will bring down an alpha similarly for the cat case. So you will have this one, and this will cancel. No, this will not cancel. Sorry. This will not cancel. That's important. So you will have e to the beta alpha minus, and here you will have of course, a conjugate here because you were in the adjoint. So in the adjoint, you will get a conjugate here, of course. And you have this one, right? But this is one now because it is a state. So this is like the formula. Yes. And let's hope that this was the most difficult part of it. I don't say that everything falls out now, but almost. Because what you have is that, these modified characteristic functions, which we have defined here. You can, for example, here, you can see it in the uh, lecture note, and you can see that you need to multiply it if you want to have this plus one ordered characteristic function. You need to multiply it by e to the power of a squared or alpha squared divided by 2. So that will kill this term here, right? So if we want to write this one, alpha in the function of beta, that is this one multiplied by this e to the plus beta squared divided by 2. So it will be just e to the beta alpha minus beta, so beta alpha conjugate minus beta conjugate alpha, right? Simple as that. And now, so this was the second step, this fallout. But I mean, it's just a multiplication, so it's not that difficult. The third step is to do this integral. So to obtain the p function of alpha, and we want to obtain it as like gamma, a function of gamma, because we will integrate out by this beta. I think we had this 1 over pi squared. We integrate over C, the complex plane, and the formula is, I mean, we have just let me check to verify that this is indeed the formula, not here. Yes, okay. But now we have to change the variables because, so alpha becomes beta and beta becomes gamma. So what we want to do here is that e to the power of beta gamma minus beta overline gamma multiplied by this characteristic function. This characteristic function is e to the power beta alpha bar minus b bar alpha, and we integrate by gamma, right? So this is fairly easy, or it looks fairly easy. And now, now, what we will have is that we can, of course, we can pull out this term here. What did I miss? No, we integrate by, okay. Sorry. This is very wrong. Sorry. Of course. This was wrong. We integrate by beta. Sorry, I was a bit confused. Of course. Otherwise it will be easy. Okay, so we want to do this integration, and we can just collect the terms. So it is this e to the beta and this one minus beta bar gamma plus alpha, right? So we collected all the terms. Okay. And now what we need to do is to switch variables, I think. Or can we do it the other way? Not really, no. So the feeling is that you will have a Dirac delta somehow here hidden, right? Because you do this phase space integral, and you have this exponential term of like beta, and beta is so it's like in the exponential, like this term is linear in beta, and you somehow expect that if you do it with real variables, then you will get some Dirac delta, right? Like some representation of the Dirac delta. So, for example, I don't know if I should go through with this because I didn't go through here as well. Not here. Sorry. There was this derivation where there must have been some kind of integral like this. Yeah, this is the one. This is the one. Okay. So maybe I just copy it. So yeah, like this. Because I don't want to derive this from scratch again. Maybe this was a tedious exercise. But you have this formula for the or you can at least if you have some integral like this, which is exactly the same integral as we have here, right? Then we can rewrite it, or we can write it as okay, so we have 1 over pi squared here, and now we have 1 over pi here, and you have this constant multiplier which we don't care about actually. The thing is that if we switch variables, as seen here, into real variables, then we can rewrite it as like a product of two integrals, but these integrals are like divergent in general. If the in the exponent this multiplier before the variable is not 0. If it is 0, then you will get like a peak, like an infinite peak. Otherwise, you will get 0. Is this okay? And so therefore what you will have is that if you integrate e to the beta alpha plus gamma minus beta alpha beta bar alpha plus gamma d beta, then you will get yeah, so this will yield pi. Isn't it something like this? Yeah. So it is this, I think. Also here it should be noted that this term or this exponential term in the complex variables can be rewritten as actual Fourier transformation. So I have already mentioned this in the lecture. So this is like the connection of these, right? And so therefore you can write this as here is this pi squared, which will drop out. This is delta of gamma plus alpha. And yes, I think that this is the one. In the special case where you have um, gamma equal to or alpha equal to 0, so the vacuum state, you will get just a Dirac delta, basically. Maybe there is some more normalization missing here, but basically that's the idea. Is this clear? What happened? Is there any question? The next lecture is gonna be easier. So I have explained all the theoretical background at this point, so there is no other like deep theory which I should explain. Next is the Gaussian boson sampling. So we derive the uh, yeah, the probability distribution for Gaussian states in the like the particle number detection probability distribution for Gaussian states. It will contain the hafnian, which is interesting, and then we will discuss the hafnian and its connection to graph theory, right? I have already explained it, and we will bring back the permanent. How is it connected to the permanent? And then we will discuss the dense K subgraph problem, and we will figure out how to apply the Gaussian boson sampling for this particular problem, and we will write algorithm, etc. So for three, we still have 3 hours. I think we can do that. I mean, it's or no, maybe we cannot. No, we can have coffee break. We can still have 2 or 3 coffee breaks. It's not a problem. Okay. Sorry for the delay. We continue now with Gaussian boson sampling. Where were we? Yeah, we wanted to continue with Gaussian boson sampling. Um, as before, I collected the relevant parts or the relevant paragraphs from the lecture note. Yes, or no? I've heard that the recording is happening. Thank you. No problem. Okay. Chapter 4, Gaussian boson sampling. Okay, so let's consider a D-mode Gaussian state now, with density operator rho, and consider the probability of detecting some particle numbers, which are here. Okay, how do you calculate this? You take the trace of this density operator together with the Fock state corresponding to this particle uh, detection outcome, right? So this is here. This is the probability by Born's rule. Okay, so in this analysis, what we can do is to first rewrite this n using the p function of this Fock state. So we have this one, this formula here, right? This is this p function, which I have already talked about earlier. I think it was before lunch, I think. And we had this crazy derivative of the Dirac delta. Anyway, I will show it again. And okay, I use this shorthand notation here. And the probability with this can be rewritten like this. How can we rewrite it like this? So what you do is to input this representation of the Fock state into the trace, and you exchange the trace with the integral. And you assume that you can do that because, I don't know, we are physicists, so we can exchange it freely. And if we do that, then you will get something like, I mean, roughly, you will get something like trace of alpha alpha rho, and you will have a p function here, this alpha, and you will have this integral, and of course this, yeah, and you will have this pi d here. Okay, so you have this, but you don't have the pi d yet, but you will have it when you recognize that this is the Hushimi Q function or Q function. So this is which is pi to the power of d times the Q function of rho. Like, yes. Is this clear? And this thing appears here. And that's what I meant when I said that if you include a p function, then you will automatically have the q function with it. Okay. So this is good. And now, is there any question? So this is like the integral representation of this probability. If you perform this integral, then you will get a number, which is a probability between 0 and 1. Okay. But then how do we do this integral? Okay. We can use the formulas, of course. So we remember that we had, at least for the single mode Fock state, we had this very similar formula like this. But now I'm denoting everything with bold fonts. And that means that these are like multi-mode. This is like a multi-mode p function. So for example, yeah, this n factorial by n vector factorial, I mean n1 factorial, etc., nd factorial, for example. And the Dirac deltas and the derivatives are also interpreted as this, with this multiplicative formula. Okay. So essentially, you get this by multiplying all the distinct p functions, single mode p functions together to get a multimode p function. You can show this because for each single mode, you will have a different independent phase space variable. So, and that's why the p function is multiplicative. Okay, but then if we want to evaluate this integral, then we can write, I mean, as I have already explained, it looks like if we input it, we have this p function here, this integral p function here, and we have a q function here, d alpha, and that means here if we input this this derivative term, so here we input this thing here, right? And I take the nth power of this, and there is like e to the alpha squared, I think, and there is like a n factorial here. And okay, you have these Dirac deltas. Then you can, as I have already discussed, you can move this derivative in front of this function, basically, right? And you move this also with that. So you also move this in front of here, and then you differentiate it together with this e to the norm alpha square exponential. Okay, and that's how you will get this. So this is coming from here, from the p function, and this is coming from the q function. Okay, but the q function also yields some, it also yields these terms, or this determinant term, and it will also kill, I think, we had a pi to the power of d, but the formula for the p function also, or the q function also kills it. Okay, so okay, this is really dense, I agree, but I can show that you can rewrite this, or I mean, by rearranging these terms, you can rewrite it to this form, which is here. And this already looks familiar because you can see that this is a Gaussian function, and you differentiate this Gaussian function by some variables, and you evaluate it at some alpha equal to 0. And you have some other terms here, but you don't care about this. And the point is that if you do this, then you will still get the hafnian. I mean, you will get the hafnian as we got the hafnian for the expectation value of higher order moments for Gaussian states, as you remember. So I think it was, yeah, it was here that that in this proposition you do this differential, you get the hafnian. The difference is that we didn't take the power, because I wanted to simplify it. We didn't take the power of the derivative here, but that only amounts to repeating the rows and the columns in this sigma matrix. I mean, it is written down in the lecture notes. You can essentially justify it by treating if you have like a second power of this derivative, you can, in the derivative, you can regard the two variable, or like one single variable to the power of 2, you can regard it as two independent variables, and that would amount to repeating the rows and the columns corresponding to that variable in the sigma matrix.
So the difference is that here is derivation with respect to real variable, and alpha is complex.
Yes, this is a very good point. This is a very good point, and that's why there is like a single modification going on here. Here you can see, I will point out with this pink, that here you have Brev alpha dagger, and here you have a transpose. Why did I do that? I did this because I didn't want to. So I wanted to modify it to look more like the original Gaussian, real-valued Gaussian function, right? So you have like this looks like something like if you want to write it, this looks like alpha vector conjugate, and you have this A matrix here, and you have this again this alpha vector conjugate here. In the other case, this was flipped in the left term, right? So this more closely resembles X vector transposed A. Yes, of course, there should be a transpose also here. X transpose A X, right? That's one thing. And the second thing is, and I can amount with this by using this X matrix. I will tell it later. So by including this X matrix here, I can do this. Okay, so the second thing is that you can see that as I have already discussed, that if you have like some alpha and you take some power of it and you differentiate by alpha, then you will get back the same differentiation rule as you had before, right? And if you do it for example, for the conjugate variable, then you will get 0. Similarly, if you differentiate the alpha to the power of n by the alpha conjugate, you will still get 0. So you can treat these as independent variables. And this is exactly the same case as here in the real case, right? So it doesn't really matter if it is real or not. You only use the property of the differentiation, right? So you can expand this exponential. You will have like an infinite sum of these x's here, or these x variables here, and you differentiate, and you still do the similar thing, or you do it similarly as here, and you have the same derivation rule. So you would get essentially the same formula. Is this clearer now? Okay. Okay. So we have this, and also I don't want to go into much detail here, but there is like an identity here, which is coming from this part. Okay. And what else? Okay, and this part, this one is coming from here. Okay. So and yeah, and as I mentioned, the X part is coming from flipping the alpha brev dagger to only a transpose. So the X amounts to a conjugation basically on the vector. And that's it. Okay. And we can also show, which is quite important, that the matrix A, which will become important later, the A is symmetric. Like an adjacency matrix. This is called A because this will, I mean, we can embed an adjacency matrix here. Okay, and but in order to embed it, you need to like, of course, decompose it somehow into linear optical quantum gates, which we have already discussed. It's a bit tedious, but you can do that. Okay. Is there any question regarding this?
So the sigma matrix comes from this Q function for given alpha, yes?
Yes, the sigma matrix. Exactly. So the sigma matrix comes from, let me show it to you, from this Q function. Exactly. Where is this? In the end. So you will have this. So this is almost the covariance matrix, but you will have to shift it and scale it. So it's a modified version of the covariance matrix. But it's important to use it here, or use this one here instead of the regular covariance matrix to obtain good results, or like correct results. Okay. Okay, where were we? Is it okay? Did I answer your question? Okay, that's good. Then, oh yeah, I already explained it, that the X plays the role of flipping A dagger to A transpose, or alpha dagger to alpha transposed. So like this. I mean, this, not that important. I'm missing a dot here. And also, uh, according to proposition 9, oh, I also forgot to mention that we use centralized Gaussian states, because we always use centralized Gaussian states, because if you don't use pure centralized Gaussian states, then you will get something. You will also have some linear term here also, which will mess up everything, and you will get a different quantity, which is called a loop hafnian, which I won't talk about now. Anyway, so we know that this differential can be written as this hafnian, and as I have already mentioned, if you take the power here, so if you take some power in this differential here, like or taking powers of the differential, then this amounts to just repeating the rows and the columns of A. And I don't know, we have already seen this when we were using the um, when we were discussing the permanent, when we had this so-called reduction. This is a block reduction. So it is happening blockwise, because you will have now, so it's a second differential here. So that's why, I mean, it's not clear now. It doesn't really matter, but the point is that you have to do it blockwise. Like you have 4 blocks in your adjacency matrix, and you do the reduction for each of them by this occupation number n. That's how you do it. So okay, what I wanted to say is that A looks something like A, no, like E, F, G, H, and the block reduction by n, by the vector n of A, is nothing else than the reduction of each of these blocks. Yes. And reduction means repeating the rows and the columns according to the prescribed occupation numbers. So yes, if you have a 2 in your in this Fock state, then you will repeat that particular row and column corresponding to the mode twice, so that there will be 2 of them. Okay, so if it's not clear now, that's not a problem. So you obtain this formula for the probability distribution, which has the hafnian in it. It is very similar to the formula for the boson sampling when we had the permanent, right? But we didn't have the determinant here, determinant of this sigma so-called Q matrix. And instead of the hafnian, we had permanent. And instead of the block reduction, we only had reduction.
So what is the dimension of this BR of A?
Oh, okay. So the dimension of, okay, the A is an element of 2D times 2D, and BR and of A is an element of, it's fairly difficult, but C to the power of 2n times 2n, where n is equal to the sum of ni in this n vector. Okay, so like it scales with the total number of particles. Yeah. So yeah, so one could say that okay, you can execute like simulate Gaussian boson sampling if you don't have many photons in your system, or if you have like a constant amount of photons in your system, but your number of modes is increasing, you can still simulate it because inside the like in the belly of the hafnian there will be a small matrix always. That's a trivial result. Okay. Is there any question regarding this? It seems like it is coming out of nowhere. I try to escort you through the derivation. Yeah, there are many missing pieces, I know, and we didn't derive everything in detail. But I think this is also enough, right? So I mean, if you want to look at the more rigorous derivation, you can check it out in the lecture notes. And and the derivation also in the original paper is also very comprehensible, I think. So they use different conventions though, uh, but yes, everyone uses different conventions for quantum optics. Okay. Oh well, also if the Gaussian state is pure, and this is our case because it is the simplest one, then the uh, this A matrix, which will become our adjacency matrix. Let's call it the adjacency matrix. It will be of this form, right? And you can write it as this. So it's B equals U and tangent hyperbolic of R. R is some kind of squeezing parameters. And U is an interferometer. Okay. And with this, you can simplify the formula like this. Okay. So it's a smaller matrix. So the size of the matrix is halved. And yeah, and that's it. So that is like the final formula which we will use. Okay. Question?
So finally, this B matrix would be the adjacency matrix.
Yeah, finally this will be the adjacency matrix. So in application, so if you yeah. Yeah, it's very interesting that for some reason they call this the B matrix, or this the adjacency matrix is B. Sometimes it is A. Anyway, let's proceed now. Graphs. Let's talk about graphs. Okay, I will just show some definitions. So subgraph density. What is subgraph density? Consider a graph. I don't define graphs because I hope everyone knows graphs. I hope everyone knows subgraphs. You can take the subgraphs of graphs, and the density of a given subgraphs, like specified by the edges, is defined as this formula. Why is this formula logical? Why do you have a binomial coefficient here? It's because if like you have your subgraph, you have a subgraph which is like complete, it's as dense as possible, right? Everything is connected with everything, then it will become 1. Otherwise, it will become 0. So it's like some kind of normalized notion of density. It's independent of the size of the subgraph in some sense. So you don't have to normalize it or anything. So that's why I like it. Right? Bipartite graph. What is a bipartite graph? I should draw a picture. So you have, for example, 2 sets of edges, for example, like this. And a bipartite graph is something like this, where you have connections between the different sets, somehow like this, but you don't have connections between, you don't have this one, right? This is a bipartite graph. So this is the thing, and of course, then you can see that you have 2 different kind of sets of edges, right? And you can also show that if you have the adjacency matrix of such a graph, then you can order the adjacency matrix, or I mean, obviously you can reshuffle the adjacency matrix however you like, but you can reshuffle it in a way that it will be of this form, like this, right? And it is still symmetric because it is still a regular, undirected, unsigned graph, 0, 1, with a 0, 1 adjacency matrix. Yes. Okay, so this is clear now. Next definition, perfect matching. And this is all the definitions I have wanted to say. Okay, so let's consider like the very same graph. Okay, consider the very same graph. I will delete this. And no, I will draw another one. Okay. So what is a perfect matching? We have already discussed this. So, but we didn't discuss it in terms of graphs. So graphs are somehow connected via edges. For example, you have these connections. Yes. For example, this one. And you want to determine the perfect matchings. What are the perfect matchings? The perfect matching is that for each, so one matching is a pairing of the vertices such that the matching, so between the vertices, you will have exactly one edge. And in this case, we have, yeah, so we don't consider 2 edges. So yes, so for example, this one is a perfect matching. But this one, where you have this is not a pairing of the vertices because you don't have an edge between them, right? And you can also consider that, for example, I write with this pink. Okay, so this is still a matching, but how can you make another matching? You can make another matching like this, right? And I think this is all the matchings. So this is we have 2 perfect matchings. So one is the green and the other one is the pink one, right? So in this graph, the number of perfect matchings is 2. And sometimes it is interesting for us how many perfect matchings does a graph have. Okay. Is this definition clear? Question? Comment? Okay. And we will denote this by PM of G, like this set, like the set of vertices paired together is the is the PM of G. We will see that. Okay. It's clear now. Okay. And now, yes, what I wanted to talk about is that okay, maybe we should draw some graphs. Maybe I should start with the hafnian, because the hafnian we already know, and let's consider this one first. So in the hafnian definition, what you have, let me say it again. So it's the hafnian of an adjacency matrix. So if you apply this function to hafnian, then it looks like this: PM of n, and the product of these ij in P, aij. Okay, this is the definition of the hafnian. And why is it that this is equal to the number of perfect matchings? Let's go through this example. Okay. So we had this example, right? We had this graph. I don't know, maybe it was like this, right? Yes, it's like this. Was it this graph? Let me check. Yes, exactly. That's new. It's clear. Then the formula is clear. You understand.
But the definition of hafnian is for arbitrary matrices, and
Yes.
and this relation of perfect matchings works if A is symmetric 0, 1 matrix. Yes, if it's
It's a symmetric
adjacency
zero-one
matrix. Yes.
Generally, it works for any symmetric matrix. Yes, and that there is no like yeah. So here, okay. So the formula. So why the formula works is that you enumerate all the perfect matchings, considering like uh, the case when it is a complete graph. So everything is connected with everything. So you just consider this, that you enumerate all the matchings. So for example, let's say that your first matching is something like this. This. Will it yield a contribution to this sum? No. Why not? Yes. Yes, there is a zero. Okay, let me show another one. So if we do this, will it contribute? Yes, because in the adjacency matrix, because they are adjacent, you will have ones here, right? And you multiply them together, and you will have a one, and that counts a single perfect matching.
Another question: there is a PM of what under the sum?
PM of n, or yeah, sorry. So A is an n by, so it corresponds to an n by.
So you wanted to say that you have PM of full graph.
Yeah, so the PM of the full
graph here.
complete graph.
Because I mean complete, yeah.
Yeah. So evaluate it for
yeah.
complete graph, and then you will, you can count up how many pairings you will have.
So basically matrix of ones, because matrix of ones.
Yeah. You can say that. And in the diagonal you have zeros, but anyway, that doesn't count here because you don't count like edges with themselves. So
Look,
in the Hafnian formula, the diagonal doesn't play a role. That's okay. So this is okay. So these were also ones, but because we multiply with zero, it comes out. And this green one is not a perfect matching. because we don't have an edge here. But for the red case, so these are you have edges here, and it is a perfect matching. Is it clear what is happening here? Okay. Okay. So 1 hour has passed, I think. Or did the 1 hour pass, or we started at 15? We started at 15. Okay, so I can continue for 15 minutes now, I think. Or we can always have a break if you are tired or something. Okay. So and yeah, maybe we can make it homework as well. But the statement is the non-trivial statement. I mean, it's kind of trivial if you think about it. That if you have like if you have a bipartite graph, so if you consider a graph something like this, like let's do it, and let's do it for a simple case. And you have let's say that like this. So this is a bipartite graph. And the statement is if you want to compute all the possible or the number of possible perfect matchings, then that will be the permanent of this B matrix, which is called the bi-adjacency matrix for bipartite graphs. Sometimes it is called like that, right? So one can argue that that if you do these kinds of pairings, or I mean you enumerate all the pairings, you notice that you couldn't pair the blue ones with the blue ones. That's why you don't have you have all these zeros here. So you have the zeros. How should I write this? You have the zeros here because you in that particular group. So in the blue group, you don't have any connections between themselves, and in the green group, you don't have any connections between themselves, right? And you just enumerate all the possible. Let me include another. What? Yeah, let me include another one because it might be easier. So yeah, so you need to enumerate all the possible perfect matchings, and you can, I don't know, have many possibilities here, right? So let's make it homework, I think, because it's like very pretty much the same argument, but instead of the number of instead of the perfect matchings, you will have permutations in the sum. So you recover a very similar sum here, but instead of the perfect matchings, you will have permutations. That's it. And in some sense, you can see that the hafnian, this is also a very general fact, the hafnian of this matrix B transpose B, right, is exactly the permanent of B. So that means somehow that the hafnian is more general than the permanent. But for the permanent, we also know that it is very difficult to compute. So the hafnian must also be very, very difficult to compute. Okay, so this is like the connection of the hafnian and the permanent, and this is how you see that the hafnian is must be difficult to compute because of this formula. And if you okay, that is good, and we have time for the next one still. Oh yes, oh yes. So consider the okay. So consider the following problem: that you have a graph, and suppose that we have some number k, which is less than the order of the graph, and the problem is to find a subgraph or find a subgraph of k vertices with the largest density. There could be many, by the way. So it doesn't need to be unique. The density I also defined, so it has like basically the most edges, like k edges. You have to find k edges for which, if you connect all the edges through the original graph, then you will have the largest density. That's the task. And you can also see that, I mean, you can also consider why it is a difficult problem to solve, because you cannot really iterate over all the possible combinations of all the possible edges. It's a huge number in general. So you have to do something else. And people have been doing, for example, stochastic algorithms for that. So you can generate guesses for dense subgraphs, and then so this is called the exploration stage, where you generate from some probability distribution some kind of uh, um, possibly dense subgraphs of a given graph. You generate a set, and from that you can choose the densest one. The density you can calculate easily, right? So if you are given a subgraph, the problem of calculating the density is easy. And then you can, I mean, you can also mix it with other strategies. For example, you can do the following: that if you have like this k subgraph, you can choose a number, for example, L, uh, the number of vertices which you will keep, and you will modify the graph according to the original graph. So it is like partially modifying the graph or the subgraph, and maybe with that modification you will obtain a denser subgraph, or maybe a less dense one. And in this stage, also in the exploration, but also in this tweaking or this exploitation stage, you can use the Gaussian boson sampling to generate more dense subgraphs. Okay. So and this is how this tweaking algorithm goes. Yeah. So the exploration I didn't really. Maybe I should have started with that one. Um, I didn't. I don't have it here. Why don't I have it here? Okay, going back. Going back. Okay, so connection density with perfect matchings. Yes. So, I mean, I don't want to write down formulas here, but you should feel that the number of perfect matchings in a subgraph is in correlation with its density, right? So if you do Gaussian boson sampling, in the Gaussian boson sampling probability distribution, so if you uh, like look at this probability distribution, that is somehow proportional to the hafnian of this one squared, and that is in correlation with the number of perfect matchings, number of perfect matchings in this subgraph uh, reduced by n, or specified by n. N is the occupation number which we detect. You could ask the question, what if there are multiplicities in the occupation number? Do you take this vertex twice if you have like any multiplicity in n? And you don't. I mean, you cannot. And the thing is that in these setups, we consider the case where the squeezings are very low and you have very low particle numbers, and most of your samples are just zeros and ones. This is called the collision-free regime. So anyway, so you see the connection with the Gaussian boson sampling probability distribution with the number of perfect matchings. That is obvious now at this point. And so the idea is that the more the perfect matchings, the more the density of the subgraph it is. Because yeah, I mean it's obvious. So if you write down a graph and you check out if it's not that dense, then you cannot really do many perfect matchings because there are not many edges through which you can draw the perfect matching, right? So yeah. On the other hand, if you have lots of edges, so for example, if you consider a complete subgraph, so that every vertex is connected with every vertex, so like you have every edges, then you will get a pretty large number of perfect matchings, which will be like the so if the size of this subgraph is n, then the number of perfect matchings is yeah, let's call this subgraph n. So PMP of S is n factorial. It's a double factorial. I mean, it's by a simple counting argument. So you count the number of pairings in a complete graph, right? So it explodes. Whereas if you have like an empty graph, then it will be zero. So that is like the intuition. But this intuition has also been made um, explicit, I think, recently. There is a formula connecting the perfect matchings and the density, or at least a bound. Yes. So I wanted to say this, and we can exploit this for generating dense subgraphs from a graph, right? That is like the basic idea. Is this clear now? Because this is like the most important idea here. Okay. Okay. And yeah, I also explained this densest case subgraph problem. So what we want to solve with this Gaussian boson sampling is that we want to sample these dense subgraphs, and we hope that we will get the densest one, or we will, yeah. Although we cannot check it, but we will be able to get dense ones. Yes. And here you have this algorithm which we will implement. So this is like I mean, maybe we could also read this now, but in the hands-on session I want to implement it basically with you. Maybe it's easy if we go through it. So if we have like a graph and we have like an adjacency matrix, that's okay. We take its subgraph and yeah. Okay. I thought that there was a typo. We will denote D by the number of vertices in G, and K by the number of vertices in the submatrix, and let L be a parameter of this algorithm, which is the minimum number of vertices to keep. And then what we can say is that, okay, we can start from this S submatrix. It has a number of vertices K. So we want to generate another subgraph, which is similar to some extent to this S submatrix, but also different. I mean, maybe it has more density. That's what we want. So randomly, what we do is that we randomly pick um, a smaller L-vertex subgraph, which is called R, from the Gaussian boson sampling distribution. So we include this adjacency matrix into the Gaussian matrix setup. So this adjacency matrix of the submatrix, and then we sample this probability distribution. This notation. I should have written like I should have had like a very different notation. Anyway, because it's not consistent now. But anyway, so we sample from this distribution, and we expect that okay, this will be a dense subgraph. So we should keep it. So we should keep these elements, and then we pick a uniform random number of the remaining vertices from S, and we extend by it. Okay. So we extend by this M, and this will define this J keep, which means the maybe I should have written S keep, but anyway, so this is the subgraph that we will keep, and this will have this many vertices. Okay, so this determines how many we keep, and the next one is generating T. What is T? Yeah. Okay. So from T, we will also build this G replace. Like, yeah, so we replace some parts of the original S by G replace, and this G replace is coming from T. So we also sample from the original adjacency matrix. So we are not considering the subgraph here. We are considering the original adjacency matrix, and we calculate or we sample dense subgraphs. And then we randomly reject M of its vertices, and this will define also a subgraph of this many vertices. And the problem is that if G keep and G replace share any vertices, I mean, we could merge them as well, but the original algorithm said that we should repeat this step. I mean, it's logical, because if we would join these, then the number of vertices, the k, would reduce. So that's why we should repeat this step, but it's okay. And the output subgraph should be this one. So that is like a tweaking part, or a tweaking thing, tweaking algorithm. And we can use this for optimization. So the idea is that if we are able to modify the subgraphs with this, and probably, I mean, if we consider this algorithm, it suggests that the new subgraph will be denser. Then maybe we can do some kind of optimization algorithm, for example, a simulated annealing. And we can say that we immediately accept the new subgraph if it has larger density, and with some probability we also accept it if it has smaller density, something like this. And we execute this algorithm, and I don't know, we decrease the temperature as we increase the number of iterations. So that could be like an optimization algorithm. If we have time, we can write it. Yes. And is this clear? What is this algorithm? Or questions?
So I understand. I mean, I understood it as like the first step, like R step, is basically local exploration around this subgraph S, and the T step is one that uses the entire graph. So you have these
Yes.
two like exploration around subgraph and exploration from the entire, or probing from the entire graph.
Yes. So exactly. So consider this, for example, that you have this, or is it okay if I draw something now? I mean, okay, so this is a star graph as of now. Okay. And for example, let's suppose that we have S is this one. This is almost complete, by the way. So S is this graph. And okay, so the algorithm goes as follows, that it says that, okay, we should keep L vertices, right? And we sample this. Like, let L be 2 or something. And I don't know, it could be anything because L is 2, so I mean it should be an edge. So it's very unlikely that it will not sample these ones because they are not connected. So in this example, it will sample this one. This is something which we keep. And also it says, if we go back, it says that we should generate a random number, a uniform random number, and we uh, extend, I don't know, extend this by the remaining vertices. Like, so for example, if m is, for example, 1, we just randomly generated it. If m is 1, then we extend this by, for example, I don't know, this one here. Right. So that this is G keep. We keep this part. Now, what we will do is we will generate another subgraph from the original one, right? This has been cut off for some reason. Okay, so we will generate this, and we will need k minus L. So k is I didn't mention, but k in this example is 4 because Wiener started from four edges. So we will need now one edge. So it will generate, I mean, k minus L. So it will generate a 2-edge subgraph. And what could it generate? I don't know. It will generate from the remaining, or yes. For example, it could generate, let me denote it by 2. Okay, because k minus L, the length of this D subgraph, or not length, but the number of vertices in this is k minus L, and this is 2 in this example, right? And we randomly reject some of its vertices, and let's suppose that, okay, maybe this is like a bad example because here, if I would reject um, this vertex here, then there would be a sharing of vertices, which is bad. So I will just cancel this one. So let's suppose that this is cancelled, and then, okay, I can just delete this. Okay, maybe this was not the best decision. You have this, and this is G replace, right? You have G replace and you have G keep, and so the new graph will be the union of this, which is this. Okay, that's how the algorithm goes. Should we have a break? I think this is a good point to have a break now because, yeah. Okay, so we were here, and there is still one thing that I wanted to talk about, which is how to decompose. So if we have arbitrary adjacency matrix, then how do we decompose it to obtain a interferometers and squeezing parameters? And we can do this by the Takagi-Autona decomposition. I don't want to go into details here. So I just want to remind you that you have these B matrices here. If the Gaussian state is pure, and yes, here we have these B matrices, and we have written, or we can show that this is U and this diagonal matrix here and U transposed, multiply together. And we want to do it reversed. So like if we want to think reverse, we are given this B, which is a incidentally it's a adjacency matrix. What is U and what is the R vector? And that is what we ask, and the Takagi decomposition gives it to us. But we don't need to do this. I mean, this Takagi decomposition is also implemented in Picasso, but also we don't have to call the Takagi decomposition necessarily. Okay. Okay, so exercise, the first exercise is this, that we have to show that when the Gaussian state is pure, then this A matrix can be written as these blocks, so like the direct sum of B and B conjugate. I don't think that we should do this now because then we won't have time to code, and this is like something which could be done manually. It's also everything can be done manually, but yes. So now let's do some coding. So first things first. Okay. Okay. First things first is that uh, I want to yeah, install Picasso, the new version of Picasso, because I included the um, Dask in it. Like we can execute it with Dask and we can see if it's faster or not. And also if you want to execute it in a CPU cluster, then I show it to you how to use Dask. So install the new version of Picasso. It is Picasso 6.2.0. Okay. And the next one is this network X. So the thing is that there are not many libraries or not many. Yeah, this is the library for handling graphs in Python, basically. And we need to install this. But it is already installed for me. Is it okay? Did you manage to install all of these? So really? Okay, okay, then okay. That's good. I didn't know about this. But yes, see, okay. So networking X is already included. That's good. Okay. Um, then this exercise, okay, so this was an easy exercise, right? I shouldn't have. I didn't know this. Why do we use this? I don't know. Okay, so consider this graph with this adjacency matrix here. Also, you can generate a random graph, but oof, yeah, this I need to copy from the exercises. So let's have this graph here, right? And okay, I want to open some code, and what I want to do, it is like fourth exercise. What I want to do is to input this adjacency matrix. Of course, I need to import NumPy. Okay. I know that I will need to use network X as NX, and I will need to use Picasso as PQ. Okay, network X, it might not be needed for the first for exercise 4.3, but I will import it because later we will need it. Okay. Did you manage to do this? Okay. So that's good. And now we want to simulate Gaussian boson sampling with this adjacency matrix embedded into the Gaussian boson sampling. And what I will do is that I will create a program. I will initialize with a vacuum, and I will include sorry. I will include, actually I can do it in the same line. pq.graph and adjacency matrix. Okay. So I specify this adjacency matrix, and the mean photon number can also be specified later. That sets the number of photons to be, on average, the number of photons to be detected uh, in the samples. Yes. And we need to instantiate a simulator. We need a Gaussian simulator. We can specify the D should be the length of the adjacency matrix. And what else do we need? We need to execute it. This must be this program. And the shorts can be, for example, let's make it 20, right? And I will have a result. I will execute it. So this is the final code. Just to show it. Gaussian simulator, yes. Okay. Did you manage to execute it? So I will execute this. Hope it will not run into a error. And we will see the results. Sorry. Ah, yeah, we didn't do, yeah, photo number detection. Sorry. So we need to do photo number detection. Yeah. Sorry, I missed this. So yeah, the photo number detection is like key in Gaussian boson sampling. Particle number measurement, that is the name. Yeah. Yeah, now we have samples. Result. Okay. Okay, this is like very dense, right? So there are many multiplicities here. What you should know is that in these samples, for example, if I take the, let me zoom in and let me delete this one. Let me zoom in. So here, if you look at the first sample here, that is good, and the ones will mean or where on the in the place or in the index where it is one, that shows you which edge should be taken into account, right? So this is like that, not the indices of the edges, but like it highlights the edges, right? Sorry? Yes, this is, yeah. Yeah, this is like this, yeah, position encoding of the edges. So like if you list all the edges, you can see that the it highlights the first edge, the fifth edge, the seventh edge, and so on. So we need to convert it to this index representation. Is it clear what I'm saying? So what we need to do, I mean, of course, um you can do that. You have this method which is called two subgraph nodes. you will call it, and it will transform the samples. Okay, and if you two subgraph nodes and underscore between the words or underline. And yeah, so we can put these two together and we can see what is the difference. So here you have uh, the vertices which you want to include, they will have ones, like they will be labeled here in this sample with one. But we can convert these ones where the ones are appearing in this sample with their indices. So this is like an equivalent representation of that, and that labels the indices, the exact indices of the edges. Or sorry, not the edges, the vertices. Sorry. Is this clear, or did you manage to do this? Okay, so the no, no linear order. No, this is a one by one mapping.
Pardon?
This is a one by one mapping.
Okay, but fourth node. Ah, okay, those are nodes that are okay. So you go through the edges and then nodes. Okay.
Yes.
Oh, it's already okay. Okay.
Multiplies nodes. Yes.
Um. Yes, exactly. So say if you have multiple ones, then you will take, yeah, multiple ones here. If you have more photons, if you have collisions. Okay. So this is equivalent to mp.var. You take this one, this sample here, and you see where it is one, and it will return with the same array. So it asks where this array is one, basically, and it will return within this is where it is one. That's the yeah. And from that way you can also reconstruct the sample. So I mean, knowing how long is the sample, but or knowing the number of modes, you can reconstruct it. But it doesn't matter now. Is this okay? Kind of. Okay. So we have this. So um, let me copy this one to the script. So we have dense subgraph nodes. And okay, what I wanted to say, okay, I will have this, but I wanted to copy this. And let's take the first one. So this is a subgraph, or this denotes a subgraph, right? And um, for this, or in order to obtain like numbers and obtain like the representation, or for example the adjacency matrix of this graph or anything, then I mean, of course you can do it with NumPy as well, but it is convenient to use network X. For example, you can use network X to let me go to this. So nx dot to NumPy array. No, from NumPy array. From NumPy array. and you take this adjacency matrix, and this will adjacency matrix, and it will return with a graph. Okay, this is like the network X object of a graph, and the subgraph can be represented by nx dot, or maybe graph dot subgraph. I'm guessing here. Yeah, this seems to work. So you have a subgraph here. This is also a graph, and this is different from this one. And you can also calculate the adjacency matrix for this as well. So we don't necessarily need this adjacency matrix of this subgraph, and we can print it out. This will be a smaller graph. Hopefully there will be many. Graph has no nodes or edges. What? Two-side array. It's not possible. Or maybe it is. It is possible. Okay, everything is possible, yes. No, now it works. Okay. Yes, yes. So now it works. Okay, this is like a very small adjacency matrix, but we can calculate the density. We can also calculate the density of this subgraph, and we can print it. So like density. I delete this because I don't need this. Let's calculate the density. Oh, this is pretty dense. Like this is the densest possible. This is not that dense. Okay, let's go through all of these. So like let's write a for loop. For I in range shots. Let's make a variable shots. Tell me if I should stop or I should slow down. Over what? What? Yes. Okay, so maybe the language here is no, the sample is a different thing. The shots is like the number of shots. Yeah, so it's so that there is no such thing as shot, a single shot. A sample, there is a sample. So okay, so yes. Question?
Yeah, sometimes I've got when I run the several times I've got error like graph has no nodes or something like that.
Yes, that
That's
could happen because it could happen that you yes, that your graph doesn't have nodes because you generate so the GPS will output the vacuum as a sample. So all of them are 0. So if you look at the samples, some of them are all 0, and that is.
You actually have to program this loop.
Sorry.
You have to program this loop actually. So
yeah. So if length of this thing is 0, then continue. Do you like this? Very good code. Clean code. What? Okay, 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 okay. Okay, 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 let's do it like this. I don't like to do this. I think this is cleaner. So okay, so if somebody would do this like in a code base with like 20 developers, nobody would understand it. So I mean, because okay, you don't know the type of this. Like if you would write something like this, it could be anything. It could be a none, it could be an empty tuple, it could be an empty list. Anyway. Okay, let's do it like this. But it okay, but this is very particular for Python. So okay, but okay. Okay, let's do it like this. Not many. These are not very dense. What is happening? Density of this subgraph. I don't like this. Sorry, I don't like this. It's so if the length of this is 0. Yes, okay. You lie to us. Okay. Like go back. Okay, so okay. 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 Aha. It's not empty. Okay, okay, so I don't know. I mean, don't rely on this. I mean, okay, maybe it's Python version dependent. Ah, yes, let me show the code. Yes. Mm-hmm.
So I have one question because we are sampling something here, yes, using Gaussian simulator. So what's the mean number of photons in this sampling?
Very good question. The mean number of photons is specified by this mean photon number variable, and this is by default one. You can set it to 0.1, for example. Let me run it. Oof. In the graph. Yeah, because okay, so there is like um yeah, like a freedom in embedding this adjacency matrix. You can scale it by any number. And the scaling amounts to the adjustment of the squeezing parameter. So and that amounts to the number of photons. Yes.
Okay, but even so you're saying that it defaults to 1?
Yes.
Because I doubt after seeing the samples that the mean number of photons in the samples that you shown us was 1.
Okay.
Right?
Okay. That's a good point. No. So like average per mode. So like it could be 4. It could be 4, but it could be
That's vastly different, average per month than average.
Per move, of course.
Okay, then it probably okay.
No, one doesn't make sense here because then we would have.
That's what I
Yeah,
said.
yeah. Like you get to 0.1 here. I demonstrate that it will be sparser. Will I see that it will be sparser? Um, yeah, maybe if I print out the samples after this. Um, yeah, but these are also small. I mean, we didn't filter for the length of this or the number of vertices in this subgraph. So result samples. This is not very. Yeah, this is much sparser. Yes. Okay. Um,
Okay, if I may just say something about the interface. It's really odd that the result does not return the list of samples as a samples.
it does.
No, it
Result.
returns array.
Sorry.
It returns NP-array
And
and not list of samples.
is it
So there should be object sample.
there should be what?
There should be an object sample. It is exactly what D-Wave does. It returns you the dictionary, or I don't know, maybe tuples. I don't remember now, but basically what is the result and how many times it repeats. So sample and multiplicity.
You can also do this with the result object. There is like this result dot I don't know what result dot get count. Uh, can I check it somehow? I will check it in the source code because I have it. Oh, not in the source code. It's a new thing that we yeah implemented. We don't have it now. Okay. Anyway, sorry.
No, just there's a comment for like the style, because basically it is rare that in Python you iterate over integers or this kind of range. You iterate over collection, like the same you do in C++.
Okay, but you can iterate over the samples here as well. So if it's a NumPy array, then what? You iterate over the NumPy array, and it will return the rows of the NumPy arrays.
Yeah, of course.
So functionally, it's the same. I mean, I don't consider the types. I'm a Python programmer. I mean, if it looks like a duck and it like sounds like a duck and
yeah, it's a line. Yeah, it's a line in Python actually, but yeah. That should be. That's the reason I don't like Python actually. Sorry.
Honestly, I don't like it either, but yeah, in scientific programming, it's ubiquitous. So okay. Okay. Anyway, can we continue? I don't know how much time we have for these things because up to us basically. But somebody will be leaving in 15 minutes. Okay. Let's sample subgraphs using the particle number immersion. We have already done that. Okay. Okay, but what we want to do here is to like filter it to have like length of. I mean, first we have to filter it to be collision free also, and we have to filter for length k. So like I don't know. Let me write a filter function on these subgraph nodes. Okay, and we can say that for subgraph in maybe this is not the good or the proper naming of this. Like this is the result, and we say that if the length of the subgraph is equal to the length of the unique, or taking the unique, which is like taking, like if you have multiplicities in an array, then it will take one representative of that, of the multiplicity. And yes, we filter it like this. And what filter do we need to use? And it also has to be k. I don't know if it works in Python. Let me do it cleanly. And it is k, and I will specify this k. Then we should append it to this list. Result dot append subgraph, and we should return with this. Is it okay if it so now it will be a list. So I wrote this filter function, and let me also specify here that k, let's say that it should be 6. So we are searching for 6 vertex subgraphs which are dense. So yes, no, it will work. Okay. Well, it's the same k basically. I just don't want to make it depend on a global variable. I mean, also I can refactor it. So if it's well, I think that yeah, issues can happen, but I think here it works. So now, yeah, there won't be any collision. So okay, so if you have some variable outside and also inside the function, and you want to use the same variable with the same name, it of course it won't work. But if it sorry. Okay, so I rewrote this a bit. Maybe I'm a bit quick. Yeah, so I wrote a filter function which filters out the uh, the collision-free subgraphs which have length k. I know that, so I wanted to write enumerate here, and then you will have an I here. So this is okay. So it is only collision-free if there are no multiplicities in the subgraph vertices. Yes. So you can have multiple photons in a mode, but we don't want to work with those. Well, we don't want to.
But from my point of software engineering, it's dangerous because you use a feature that is not obvious in two subgraph nodes. You have to immediately know that two subgraph nodes makes multiplicity of your it multiplies the node multiple times, and that subgraph. Okay, that's that. Yeah, you have to rely on this information.
Yes.
Which is not obvious because.
I mean.
Yeah, but when it's a set, so we don't know that it is basically a multiset. We could assume that it's a set because no subgraph nodes should be a set.
It's a list.
Yeah, but I mean, mathematically should be a set, not multiset.
Okay.
So
these two subgraph nodes should. Okay, but what kind of graph do we talk about? Because graphs, I mean, you could, yeah, say that, okay, you have loops in your graph, right? So, not loops, so you have edges.
Multiple edges, like we want to have multiple edges in
see,
between two. Yeah, so that's. I'm not. Look, of course it works. I'm telling you from the point of view of user that look, the assumption is if I have a subgraph and it is written in the function name and I have nodes of this subgraph, it is a set.
Yeah.
You're commenting on an ad hoc function.
No, two subgraph nodes. I'm commenting about the behavior of the.
It's like an implementation.
Yeah.
Yeah, and it is explicitly here that it includes the counts because we don't. Okay, so we don't want to lose information, but I agree that it should be a set.
Okay, yeah, but or a multiset, which is perfectly fine.
Yes.
But it's not clear from list of int.
Yeah.
Yeah. Look, I have grayer beard than you, and I made many mistakes in my life writing software.
Okay.
And that's the reason why I'm, from the user point of view, you need to reduce the amount of assumptions that a person, the user, has to make. And
yeah, so maybe it could be a set. So it's not very important that it's
yeah, that should be a set, obviously. Of course, in Python it works, but then when you filter in this way, okay, that's strange. Like strange because you make this particular assumption about your implementation, and yeah.
But it is described in the docstring. But yeah, I agree that it's like it's yeah. It could be so like it could be a set. So mathematically, it should be a set. I agree.
Yeah, but at the same time, yeah, mathematically, and at the same time, it is logical that in the code it is a set.
Yes. Okay. Should we change? I mean, I could change the API for you.
No, I'm just complaining, and I'm not saying that it's up to you to decide what do you want to do in API, but this is like the moment when I mean I don't understand the P and Q integrals, but here I can at least from experience tell you what is strange here, because it raises the complexity of the code, because
yeah, I see.
you have to carry additional assumptions in your mind rather than refer to the general case, because it is not a graph. It is some. It's strange object. It's a strange object.
Yeah. I agree. And also, if we anyway depend on network X, then we could also return with network X objects anyway, right? So it's also, yeah, feasible to do. Yeah. That would have been easier. Okay. Anyway, We have like 4 minutes, I think. So, but you accept this code, right? That
Logically, yours, of course.
pretty good. Also, it's like we are not developing software here. Of course, the two subgraph nodes is like part of a software, and I agree that it is like it could be a set or a multi-set, and it's. But of course, so in like many algorithms which are implemented in Picasso, yeah, you could use a set or a multi-set logically, but you don't use it because it's not that fast compared to using NumPy arrays. Like, you know.
Yeah, of course. I mean, obviously, there could be uh, some optimizations that usually should be explained or just hidden from the user.
Yeah. Yeah. Okay. Let me execute this. I will execute this and see what's the result. Ah, there is no result. Ah, because the mean photon number is still pretty low. It's too low. Yes. And also ideally, because we have k equal to 6, we want to have the mean photon number to be k divided by the length of the adjacency matrix to maximize the probability that we will have a uh, good subgraph. And maybe let's take more shots. Let's take 100 shots. And maybe, not very dense. And very ordered. I agree. What is happening? Hmm. Maybe this filter function is not good after all, right? And also I don't understand why we have 8. Okay, so this is the result. I don't believe that it doesn't contain like this is for example uh one which would be good. Okay, we have this. Ah, okay, sorry. This is see, Tomek, this might not be good here. Yeah. I don't know. Let's call it X for now, or I don't know. Thank you so much for attending. See ya. Um, I need to debug this, but okay, this is the subgraph nodes. Okay, and we want to filter them. So if we filter them, then we will get much less. Maybe this unique function doesn't work as well as I thought.
That was my point, that this complexity is already large.
Yes. Um, but why is it? Go to the code. Yeah. So the problem is that. Mhm. No, so my problem is that maybe we shouldn't have done this. I mean, this is like a lot of coding already. That okay, so this is a list and list of lists. Sorry, and the filter should return with with a list of lists also, but it returns with a list. That's right. It's not good. You see, because yes, to the filter I pass the dense subgraph nodes. So this list, it should go through this list. That's that's a good point. That's a good point. And the complexity was not in this for if.
The complexity so in the entire function, and it should just act row by row. So the filter you should apply, it should be a predicate that uses filter to filter the list. The filter is, this is a pattern that could be more applicable here because you build a list, which is why? What's the point of building this list here? Just logical predicate is unique or whatever. I mean, is node unique or
I could define functions
yeah,
to do that.
yeah, the predicate, which is like that truth valued function, Boolean valued function.
Yeah, and I could also use like a built-in filter function.
Yes, or just least comprehension.
Or just least comprehension, right? Yes. Okay, that you can also do, but okay. So I don't know. So maybe this works. Maybe this doesn't work. It seems to do something. So for example, if we, I don't know, we can also print the subgraph here, and we can verify that this is indeed, I don't know, a dense subgraph. 6 nodes, 12 edges, not that bad. I don't know. Maybe if we run it a second time, then we won't get a better one. But we don't get much anyway. But we can do it for many more. I hope we will get more results. So we have more results seemingly, and the density is quite good. I mean, why not? And also, so if we would continue with this, or how we would continue, we would use this tweaking algorithm. So we would choose one of these graphs, or we can choose multiple of them. I don't know, but let's choose one of them, and we could tweak them, for example. And this tweaking can be used, for example, in a simulated annealing, or yes, a simulated annealing algorithm. But of course, you can take many of these dense subgraphs, and I'm sure that you can come up with an evolutionary algorithm, which also tries to, maybe that is a bit of a stretch, but there are many of these stochastic algorithms which could be used to find dense subgraphs, and the GBS is just a part of this. Okay. And also it should be mentioned that there is like a quantum inspired classical algorithm relying on this probability distribution. So you can approximate this probability distribution, not very well, but somehow you can approximate or come up with a probability distribution which also gives you dense subgraphs, and you can also use that algorithm or that probability distribution in this problem. So yes. Sorry? A tongue? I don't think so. No. It was no. No, it was done by Nicola Quesada and co-authors. So yes. Anyway, so I think we don't have time for more. So the next thing would be to implement this GBS tweak algorithm and also use the GBS tweak algorithm to implement the simulated annealing algorithm. But I give it as a homework, or you can check it in the paper. I guess there is like a code in the paper, in the original paper, and I could also send it to you later. I mean, I have an implementation somewhere, so yeah. So is it okay if we just, I don't know, don't continue? Okay. Okay.
But it would be really nice to have maybe the codes you finished here, or something would you consider to, or for example the corrected or repaired notes, if you would have time to you find some typos or some errors in the notes. Maybe not about the typos like missing dots and this kinds of, but the equations, it would be nice to have it like in the uh, correct way, correct form. Yes, for me, I will go through it slowly once more, and at least for me, it would be really nice. But I think
Yeah.
there are other who would really appreciate that. So.
Yeah, today I will go through the lecture notes again, and I will send you this PD or like this, I don't know, everything that I've written here in a PDF version. I will also send it. And what else can I send? And I will also send a code, or I mean, it will be in, I don't know, in Indico probably. I don't know.
Yeah, I think it will be uploaded there.
Yeah,
Thanks.
if that is good, yes, yes. And also I will try to send the GBS tweak algorithm as well. Yes. Okay. Thank you so much. Thank thank you so much for having me, and thank you for the organizers, and thank you.
Yeah, and so with this, I would like to thank both the Zoltans once again. I'm really happy that this workshop could be organized here, and thank you for your really astonishing work. It was really amazing to see you here all 2 days at your solely you. So it is impressive. And with this, I would like to thank all who lasted for the whole 2 days, because there were some drops in the numbers in the Zoom. But uh, yeah, so thank you for coming, and hopefully see you again at some other quantum computing seminars or workshops and whatever. So goodbye.